I've hit it. Hello, everyone. If you're coming in a bit early, welcome to our third day of our 109th annual meeting. The chat is open, so please feel free to introduce yourselves and say where you're from. And, you know, some people just talk about the weather, but just feel free to say hi.
Good morning, everyone.
Hey, Stella.
Good morning, Stella.
Are we online? Hey.
Yes.
We're live.
Wonderful. Good morning.
Let's see, Edmonton, Alberta. So Gregory Sivikoff is here.
"21 attendees right now."
Good morning, everyone. Welcome. Good to see you again. Let's see, where's the chat?
Yep, I'll reiterate for people just coming in right now, our chat is currently open, so feel free to say good morning or good evening wherever you are, and introduce yourselves and just let us know you're here. If you have different settings, you can choose to send it to panelists and attendees, and that way your message and hello gets across to everybody.
I need to send to everyone.
Whidbey Island outside Seattle. Hello, Greg. Duxbury, that's close by.
Hey, Jean Bruno.
No, I said AAVSO anyway. Hello, Dennis in Marana, Arizona.
Yes, it's very sunny here too. We had John observed his sunspots this morning.
There was none.
Oh, there were none. Oh.
I could see anyway.
Cloudy in Minnesota.
Hey, Pierre.
Ooh, all the way over in Belgium.
It looks like it's sunny everywhere.
How about in Argentina?
Sunny too, yeah.
Wow.
Great. Exotic Vermont. Yes, it is.
I used to live in Vermont.
Oh.
Hello to Vermont. Colorado, Albuquerque. I also used to live in Albuquerque. Oh, a couple of people from Albuquerque.
Oh,
Is it streaming on YouTube today as well? No, it's not. Our membership meeting streamed on YouTube and our how-to hour streamed on YouTube yesterday, but none of the presentations are being streamed live on YouTube because, you know, people paid to attend this event, and we're really excited to have everyone here. So it's not being live streamed today because it's just presentations and then our breakout sessions. Santa Fe is gorgeous.
Well, there's a place where it's rainy in Toronto, Canada. So it's not sunny everywhere.
So for people just coming in, feel free to welcome yourselves in the introduce yourselves in the chat. And I also want to take a moment to just once again thank our sponsors. Our platinum sponsors of this event are OBSTech. It's a telescope hosting company. QHY CCDs, CMOS and CCD cameras is their specialty. Optical structures, they have a lot of different equipment, including filters. And then our gold sponsors of the annual meeting and workshops is First Light Observatory Systems, and a gold sponsor of our annual meeting is iTelescope.
Good morning, Eric, from sunny California. How are you today? Eric Mamajek. I saw him, didn't I? There you go.
Yep.
You need to unmute yourself. You need to unmute yourself. Oh.
He's not ready. He's our keynote guy.
Hmm.
Leanne. Hi, Leanne. And Al Home. Yeah.
Philip, once again, is joining us from Romania.
Hello, Philippe.
Yes, we're happy to have you here once again too. Thank you. For anyone who wasn't here yesterday, Philip gave or the past couple of days, Philip gave a presentation. He was one of our presenters.
Really cool one, actually.
Hello, Philip. How are you? We've been in
Morning,
touch
Richard.
so many times.
Oh, host
Yeah,
is
I'm
not
working.
allowing.
There you are.
Hello, can you hear me?
Yes.
Oh, we can.
Wonderful.
Good morning, Eric. Do I see sunshine
Hello.
behind you?
Yes, very nice outside.
Is it?
One Sunspot group is moving off around the edge. Oh, that's cool. That's seen in Maryland by Jay. Hi, Richard Berry.
We're up to 57 people.
Yep, we're almost at the top of the hour, but we'll wait a few more minutes for everyone to get settled in.
Stella, shall I stop sharing my screen so you can do yours?
Me?
Yeah, do you want to do the initial
Yes.
slideshow or shall I?
No, you should. You should.
Okay.
I'm just here to say hello
Oh, okay.
and to listen to talks, of course.
Right.
Yeah,
then
I'm
gonna
really
be an
excited for our
extra-
keynote today, and I'm really excited for all our presenters presenting today too. It looks like we have a great lineup of talks, and I'm
Mhm.
excited for the breakout sessions, wrapping up our annual meeting today. Hopefully we'll have some good discussions. It's a great opportunity, the breakout sessions, not only for anyone who's involved in those sessions, sections already, but if you're curious about a section, to pop in and ask any questions. It's just a very casual discussion format.
If you want to learn more.
Hello to Paul. They're all recorded so we can see the ones we miss. Question. Yes, all these are recorded and they'll be up on our YouTube channel in a few weeks. And we'll be providing the information to access all of those once they're posted.
Up to 70.
And this goes for the discussions in the session breakouts as well.
Shall we get started?
Sounds good to me. We're at the top of the hour.
Okay. Welcome, everyone. It's great to see you. My name is Sarah Beck. I'm an AAVSO staff member, as probably many, or if not all of you know, because I probably sent you an email at one point or another. I've been a staff member for 30 years, and it's a lot of fun working at the AAVSO, and especially when we have meetings and I can sort of connect to all you all. Anyway, it's my great pleasure to welcome you to the final day of our 109th annual meeting, and we hope you've been enjoying it so far. By now, you're probably all Zoom experts, but just in case, we're going to shut off chat soon, so that we won't interrupt the speakers. But if you have a question to ask, please use the Ask a Question Q&A button. And then you can put your question there. Sebastian will read those to the speaker and answer the questions. We also have in the corner, if you're having any problem with your sound, there's a sound button down there. Actually, you probably won't need that until the breakout session at the end when we're, so you can chat with the other people in those individual sections. Today's schedule, it's a very full schedule full of lots of interesting talks. As you can see, there's more. And then at 1800 UT, we're going to have a 20-minute break. And then we're going to go into the 6 simultaneous observing section breakouts. So you can travel from section to section or just stay in one or whatever you like. I believe you've probably already gotten these links, but you'll see these again at the end. But these are how you get into the individual sections. So you'll have to leave this webinar, unless you're staying for Eclipsing Binaries, then you stay here. The other ones you can leave and go into whichever section you like. And then the other thing you should note is that our research poster hall is available online. There's the URL. I believe it's in your packet of information, isn't it? And also we'll have the same URL again at the end of the regular poster session. And the other thing I wanted to point out in a minute is we have, thank you of the observers. We have a list of the recipients of Observer Awards. In that packet, again, there's a link to the webpage that has all those people. You know, you guys are our bread and butter. We really need those observations. Of course, we like quality over quantity, but it's a real honor to be able to congratulate you for all the hard work we know you're doing. And the Director's Award this year went to the Harvard Business School Community Action Partners, who were a huge help with our all the work we've been doing this year on reorganizing, thinking about the strategic plan and all that. And finally, but not, I mean, I have to thank our sponsors, platinum sponsors, OBSTech, QHYCCD, Optical Structures, and First Light Observatory Systems and iTelescope. We really appreciate your support for this meeting. And with that, I will stop sharing my screen. And we're going to hand it over to Eric Mamajek, who is our keynote speaker. And take it away, Eric. You should be able to unmute yourself. There you go. And
Hi,
share
can you hear me?
screen.
Yes, we can.
Okay, thank you. Let me just get my window up here. And I'm assuming you're looking at my screen.
Yes, we are.
Okay. All right. Well, I'd really like to thank Stella and the rest of the AAVSO for inviting me to give a talk. I wanted to try to give a coherent story about an interesting object we found almost a decade ago now. It's hard to believe, and just wanted to talk a little bit about how things have gone and highlight a few contributions from AAVSO observers here. I have a long list of collaborators and students below. Especially like to thank my PhD students, Mark Pico, Sam Mellon, Aaron Scott, Fred Millikamp from University of Rochester. I recently left University of Rochester around 2016 to join Jet Propulsion Laboratory, where I'm now Deputy Program Chief Scientist at the NASA Exoplanet Exploration Program. So we're the train of PhD students here working on topics related to this has now ended. And I especially like to thank my collaborator, Matt Kenworthy at University of Leiden, and some of the slides you'll see today are from him. And he's been a great collaborator to work with on this topic for many years. And I'd like to thank Josh Hamsch and TG Tan, especially among the AAVSO observers. You'll see some of their data in some of the light curves I show here. So the title I gave the talk was Transiting Extrasolar Disks, Seeking the Circumplanetary. And what I'd like to talk about is a story of a serendipitous discovery. And you may have seen this news item back in calmer times around 2015. This was actually the front page of CNN in late January 2015 after a new result we had modeling this ring system around this object, J1407b. And I'd just like to tell you a little bit about the history of it and where it's at. So we know that in our solar system, we see the giant planets, and from meteorites and theoretical studies, we believe that the giant planets formed most of their mass probably in the first 5 or 10 million years. And the gas-rich circumstellar disks we see, the protoplanetary disks around young stars, seem to disappear after timescales of 5 or 10 million years. And when the cores of these giant planets are forming, they create these gaps in their disks. And it doesn't completely shut off the material flowing onto the star, but the material has to flow through the Hill sphere of the planet. So this little dynamical region where the planet dominates the gravity, and at a small fraction of the Hill sphere, a disk of material form. And we see satellites, right? Going back to Galileo 1610, we see systems of small satellites around giant planets. And we now know planets are ubiquitous at least in our galaxy. It's a big result from the NASA Kepler mission. And we suspect that satellites are also common. Something of the order of about a quarter of nearby sun-like stars appear to have giant planets. That's probably a lower limit. And so there could be satellites forming around, there could be trillions of satellites similar to the Galilean satellites in our galaxy. But until recently, there's been very little evidence of the formation circumstances, and we'd like to study what is going on close to young Jupiters and see whether there's any evidence of satellite formation. What are their circumplanetary disks like? What are their lifetimes like? Are there debris disk phases afterwards? Things that are similar to Saturn's rings, but perhaps much larger, much higher optical depth. We really don't know about the circumplanetary environs, except for the planets in our own solar system. Now, we didn't go into this really looking for circumplanetary objects. So where I'll start the story is we were studying the star formation of the nearest OB association, Scorpius Centaurus or SCO-SEN. If you go to the southern skies and look up over about a 90-degree wide field of view, you'll see here the constellations. You see the Southern Cross. Here's Crux, Beta Centauri. Next to here's Alpha Centauri at 1.3 parsecs, but Beta Centauri is a part of this group. And a lot of these bright blue white stars you see, naked eye stars in Centaurus, into Lupus, and into Scorpius. A lot of the bright stars you see in Scorpius, including Antares, are part of SCO-SEN. And in fact, Antares is the only M supergiant in SCO-SEN. And what we're seeing here is a huge region that's been forming stars over about the last 20 or 25 million years. And something of the order of probably about 10 supernovae have gone off from the high mass members. There's networks of bubbles in this region from supernovae. And of the order of about 10,000 stars also formed. And now most of that population is accessible with the Gaia, results of the Gaia mission. About 20 years ago, we were using Hipparcos to find the membership for objects down to about the mass of the sun. And so my group at Rochester, and in fact, going back to my PhD work at University of Arizona, we'd been investigating the stellar populations in SCO-SEN. Now, the star I'll be talking to you about today is a previously anonymous object. Before about 10 years ago, we nicknamed it J1407. It now has a variable star designation, V1400 SEN. And it's right in the middle of Centaurus. If you're looking just for a little bit more geography here, if you're looking down on the galactic plane, this is a nice map from Kevin Hardine's galaxymap.org, looking down at the sun within about 200 parsec radius. He has ISO density contours of the bright B-type stars. And so SCO-SEN is this huge region filling up this galactic quadrant over here, stretched out over a couple hundred parsecs. And so J1407 is right in the middle of this group. In the course of Mark Pico's PhD thesis work at University of Rochester, we had been using a combination of X-ray surveys, proper motion surveys, about 10 years ago to find the members that were similar in mass to the sun. We were looking for large numbers of young suns to study what was happening with their protoplanetary disks as a function of time, also to find samples for direct imaging of young giant planets. And J1407 or V1407 was just one of a couple hundred solar type members that had been uncovered in the survey. And what you're looking at here is actually the first age map of SCO-SEN. So this is a 90-degree wide region of sky. And we've just put down some color to show the average ages of these stars. These stars are mostly still pre-main sequence. They're still contracting to the main sequence, and we can use their luminosity above the main sequence as an age indicator. So most of the stars you're seeing here are on the order of 10 to 20 million years. Now, we had taken spectra that showed that this was a young star. It's lithium rich. Young sun-like stars consume their lithium early in their lives, most are lithium. And a couple data sets had become public from these large all-sky surveys that were conducted in the 2000s, Super WASP and the all-sky automated survey, ASAS-3. And Mark Pico had cross-referenced the new sun-like stars that we had found in SCO-SEN with the archival data from the Super WASP and ASAS-3 surveys. And in late 2010, the motivation was actually to measure rotation periods. So for these young sun-like stars, they have large star spots. They typically have amplitudes of a few percent, and you can measure the rotation periods. And we thought we'd be able to help constrain the angular momentum of these pre-main sequence stars. And so he had found many light curves for these new objects in the Super WASP and ASAS data. And he uncovered one that was really, really weird. Okay, so this plot you're seeing at the top, this is the Super WASP light curve for J1407. It has a huge 3 magnitude dip in it. This was in March or April 2007, but nobody had noticed it in the data set. And this was not a particularly bright star in Super WASP, and there are lots of there's certainly lots of gremlins in the light curves there. So if you weren't paying too much attention, you might dismiss this light curve. But we also looked at the ASAS light curve, and lo and behold, it had fewer data points, but it also showed that there was a large dip, a series of dips in early 2007. So we did a precursory study of this. It took about a year because we were trying to figure out exactly how to interpret this. And the first time we saw it, the first thing that came to mind was it reminded us a little bit of the eclipse of Uranus's rings that was imaged with the Kuiper Airborne Observatory back in 1977. When the rings of Uranus were first discovered, it was a series of dips, and the dips were symmetric on either side. And oops, let me just show an animation here. So if you combine the ASAS and Super WASP light curve, this is zooming in over the few year long light curve. This is zooming in on early 2007. And you can see the overlap in the two data sets. Oops. Now, if you bin them by night, you start to see some interesting features here, and things start popping up that show that there might be some symmetry. And we also saw this, what looked like a bit of a lopsided V. Okay, and this was suspicious and was our first indications might be some sort of inclined disk-like object. There had been reports of things like this seen before, and probably the most famous example that might be familiar to some AAVSO observers is EE Cepheid, which is a disk transiting a B-type star And I think it's about every 30 years, or maybe it's something like 10 or 30 years. It has a very long period. But it also has these this sort of lopsided V structure in its light curve, and it also varies from event to event. So this was the cartoon we came up with. It took us about a year to get to the point where we were willing to publish anything on this. It was such a surprise, and we weren't set up really to analyze it. So a couple of grad students, Aaron Scott and Fred Mullikamp at U of R, contributed to building a preliminary a tool for modeling disk and ring systems passing in front of stars. And this was the first sort of straw model we came up with, which required a series of rings. And so this is the paper we published in early 2012. And at the time, it didn't get too much attention, probably because of the horrible choice of title, because I wasn't sure exactly what to call this thing. And shortly afterwards, I got Matt Kenworthy interested in this. He was a collaborator of mine on some infrared imaging surveys in the 2000s, and we had an interesting conversation during an observing run. And I showed him the light curve, and he was very interested in this. And he and a student picked up working on this, Tim van Werkhoven, and they reanalyzed the SuperWASP data and really cleaned it up. And we start to see even more features, and it was what was going on during the individual nights that was starting to give some clues as to what was going on. So this was Tim van Werkhoven's reanalyzed SuperWASP light curve from 2014. And the interesting thing was during the nights, you could see these trends, and you would see very sharp features, things that look like square roots and V's in the light curve for an individual night. So even over the course of a few hours, you would see changes on the order of tens of % in the brightness of the star. And what we were able to do was you can come up with an estimate of the orbital speed of the material passing in front of the star. If you have an optically thick, essentially a brick passing in front of a star, and you know the size of the star, we know the size of the star to about 10%. It was similar in scale to the sun. You can actually come up with an estimate of the orbital velocity from the steepest light curve within the series of dips we saw. And you get an estimate of around 33 kilometers a second. That should sound pretty familiar. That's within about 10% of the orbital velocity of the Earth around the sun. And since the events were happening over about 50 some days, we now get an idea of the scale of this object. It's something of the order of about an AU. Okay, so this is the cartoon we had for the J1407 system. This was a really big set of quote unquote rings. This is clearly not something that is just similar to the ones around Saturn, the other planets in our system that are close to the Roche radius, where the rings cannot accrete into large satellites. This is clearly a different type of structure. And the other thing is J1407 is a very young star. It's only about 16 million years. So we may be seeing either primordial material or debris kicked up if there was a larger number of collisions early in the history of that disk. And just to show where some of the features of that light curve come from, these lopsided V light curves, there's now been other examples of things like this. I'll show you an example just recently found in the K2 data at the end here. But again, EE-Ceph is probably the most familiar example historically. This is just an animation showing our 2015 best estimate of the ring model. Unfortunately, the data is somewhat sparsely sampled. We've only had about 20% coverage during here. Now you see this model doesn't match all the bumps and wiggles in the night-to-night variations. This model was forcing symmetry on the disk plus rings. There's unfortunately, that is a real gap. The star did not disappear. There was a real gap in the data, probably due to the moon. And we fit most of the features there. But just to get the bumps and wiggles in the 20% of the data we had required something of the order of a few dozen rings of different varying optical depth. If the material has a similar mass opacity to Saturn's rings, you're talking about something of the order of about an Earth mass, an Earth-Moon mass of material spread out over 1 AU. So this is clearly a very different beast compared to Saturn's rings. And this is just another cartoon from that 2015 paper. So if you look at this cartoon here, there's Saturn and its ABCED rings. Way in the upper right is that tiny little fleck, and to scale for the J1407 system. Now, if you take those rings and you map out their optical depth, there was also areas that seemed to be very clean where the brightness of the star returned to normal. And so we had posited that maybe there were objects between these rings that might be dynamically clearing them. You could fit bodies up to about the mass of Mars that could clean those out. But again, at this point, I'll mention that we don't think that that they're probably symmetric at this time. Dynamically, that doesn't seem to be stable. So what's happened? Well, the observations are starting to really paint this object into a corner. If the velocity was 30 kilometers a second, that doesn't leave much room in the system, because the mass of the star is about 1 solar mass. Well, where do you find things moving at 30 kilometers a second? At 1 AU. Well, that would have a period of 1 year. Oh, well, then you would see the transits very often. Well, if you combine the historical data with the AAVSO data, we can now rule out periods out to about a decade. And this really makes things tight. This object would have to be on a very eccentric orbit, and we'd have to be catching it near periastron. And that makes for some very uncomfortable coincidences. Some dynamical work by Steve Ryder had suggested that the material, which may have to be on retrograde orbits for it to be stable in that sense, to be even remotely dynamically stable. So that paints some constraints on it. Some recent dynamical work from dynamicist Zanazi and Lai, and recently by Speedy and Lai, Zanazi, suggests that instead of a flat ring plane, what we could be seeing is a so-called Laplace plane. Basically, the material could be on orbits that is sort of ruffled or warped, where the torques from the star and the planet cancel, but not necessarily in the equatorial plane of the planet. So below is the AAVSO curve, and I especially like to thank Josh Hamsch for many of the data points on here. And I'd like to encourage people to continue observing this object because it's been such a mystery, and we still don't know really what's going on with it. This is from a recent analysis by Robin Mental, who's a PhD student at Leiden, and combining the AAVSO data, the SuperWASP data, the ASAS data, and now we have we have a few hundred data points from the Harvard photographic plates going back 100 years. We can basically rule out all the periods shorter than about a decade. So it can't be closer in than Jupiter. And we can actually roll out a lot of the orbital space out to periods of a few decades. But again, this starts to make things very uncomfortable given the required orbital velocity. And just to throw a monkey wrench in the system, we actually managed to get some ALMA time to observe it to see if we could detect it close to J1407. And we were suspecting we'd have a chance of detecting it very close to J1407, but there was actually a source about 0.4 of an arc second away, which was right at the brightness we were expecting J1407b to be. Now, we don't know if this is a background source yet. We need to get another epoch. It's very common to find background galaxies in ALMA images, but the object is also near where you'd expect it to be if it was an object that was just simply passing in front of J1407, not associated with the system, but moving at tens of milliarc seconds a year, in which case it could be a foreground substellar object with rings. So we really need some more ALMA data to see, to test that hypothesis, but maybe this object is not bound to J1407. In a couple closing slides, I just want to talk about a little bit of follow-up work here. I just have one slide for Beta Pic. There was a giant planet discovered on the nearby young star Beta Pictoris, which is remarkable in that it's 20 million years old, only about 20 parsecs away. It has this famous debris disk, and Beta Pic B was going to come close to transiting the star Beta Pic in 2017 and 2018. And with the excitement from J1407B, Matt Kenworthy and I got some funding to build a couple instruments. Oops, it looks like they got cut off in the lower edge there, but there was these small robotic observatories called B-Ring, Bring, standing for Beta Pic Ring. We conducted a survey using that instrument and have combined the data from a few other surveys, including from the A-STEP instrument in Antarctica, and we'll be publishing those results soon. But we were looking to see if there was any evidence of circumplanetary material around the planet Beta Pictoris b, and so far we didn't see anything, and we can place pretty strong constraints. But the optical depth never seemed to be higher than about 10 to the minus 4 for any material that passed in front of the star. So the other thing that got us interested in this is what you see below. This is a light curve from 1981. There was actually an interesting event that happened in the light curve of Beta Pic decades before they knew there was a planet there. And it's still not clear if these two are associated. Recently, another planet has been discovered in the system, Beta Pictoris c, which is similar in mass, but much closer in. It's possible that Beta Pic c may come close to transiting Beta Pic next year. So we're looking into that. Another similar discovery just came out in the K2 data. K2 was the extended Kepler mission data, and the Kepler observatory was able to point at some nearby star-forming regions, including the Taurus region. And one of the pre-main sequence stars there is a binary called V928 Tau. Dirk van Dam at Leiden Observatory found a very interesting feature in the light curve. This is the combined light curve of these two binary stars. There's this thing in the light curve that looks like a very inclined disk, and it's also of the order of about an AU in scale, with a minimum period of 66 days, but it must be much further out than that. So we're still following up on this object. This was just published a couple months ago. And there's also this interesting object that was discovered near the end of 2019 by the Assassin survey, this J06000000 object that was reported by Wei et al. And there's a group, including some AAVSO observers, that are following up this object. This is an otherwise boring field K-dwarf. We do have a spectrum of it. It looks like it does show some lithium, and the lithium suggests an age around 200 million years. So it does seem to be somewhat young, but the star was behaving fairly well until the end of 2019. And now it's had this very complex set of transits. It's not clear if this is some large symmetric object similar to J1407b. This may be something like the Boyajian star discovered in the Kepler data. We're still studying this object, but right now, given the time scale and the changes in brightness, this also seems to be on the order of an AU. So it's clearly not just a small ring system. It's not clear if this is from, smash up of asteroids or if this is something associated with a planet. So anyway, I'd just like to encourage people to, when you're looking for targets to contribute observations to, consider these candidate transiting disk and ring systems. They've been very interesting. I'm hoping a few decades down the road here, we'll be talking about large samples of these and trying to characterize the constraints on circumplanetary rings and disks around giant planets. And I'll just close on this cartoon image. This is what J1407b would look like if it was in our own solar system. So thank you very much.
Thank you, Eric. Do we have any questions?
Yes, we have a question here. What was the primary indicator of rings versus any other cause of variability? Did the age color of J1407 have anything to do with it, or was it primarily because it was visually similar to light curves of other rings?
Yeah, I'd say the closest analogy was EE Cepheid. That one stood out in the literature because as soon as we found it, we were looking for examples of things that look like they could be transiting disks. There had been some modeling of the EE Ceph disk that looked like it could be a couple the optical depth could be changing as a function of radius in that disk. The thing that really stood out was there are features on either side of the main dip that look like they're somewhat similar optical depth. And we were able to get a decent fit to the photometry from a simple ring system. But it must be more complex than that. And unfortunately, we've only got about 20% coverage during the 2007 event. So we may be, we've been trying to impose this symmetric disk. I'm not even sure what to try to fit to it to do something following the Laplace plane. I haven't had time or any person power to work on that. But you definitely, just simply looking at the nightly averages, you could tell that there was symmetric features, that it must be somewhat ring-like.
Great. Elizabeth has a comment.
Hi, Eric. It's great to see you and hear you talk about J1407, this very cool system. I just wanted to let everybody know that Eric has had a campaign, an observing campaign running with the AAVSO since 2012.
I'm not that old. I didn't start that long ago.
Neither am I. The AAVSO is, though, but no, since 2012. And the campaign is still running, and it's alert notice 462. So if you go to our alert notices webpage, you'll find it among the active campaigns. So please continue to follow it and subscribe to the forums for that campaign, so you can stay updated.
The observations are even more important now. We were taking some observations when I was working with some students at University of Rochester, but I don't have the team anymore with me. So the AVS observations would really help. My nightmare is that we're going to miss a 50-day event right in the gaps in the data. But if the period's longer than a decade or so, it may take us a long time to figure out that it might have been missed.
Yeah.
Great. We have one last question from Claudio Vélez. He asks, is there spectroscopic data collected from any of these candidates? He means the disk themselves, not the stars.
There is for this new one, J0600, there was some spectra, and so far there hasn't been anything seen that I'm aware of. Beta Pic, when we thought the Hill radius of the planet Beta Pic B was passing close to, or partially in front of Beta Pic the star, there was a lot of spectra taken in 2017, 2018. It has been very confusing because the Beta Pic system has these absorption events happen all the time. There seems to be exocomets, essentially. There is gas in the system, and it has made the interpretation quite difficult. We were wondering if we would see gas associated with a circumplanetary disk, but so far that doesn't seem to be the case. But that system has just been too busy in terms of the absorption features. J1407b, we certainly have spectra, but the main event was in 2007. We weren't even aware it was a member of SCOSEN in 2007. Again, it was found in the archival data.
Thanks,
and,
Eric.
Just another shout out to make your data, post your data, make it public, put it in archives. This really was the Super WASP and ASAS data made this possible. You never know what's hiding in these data sets. And I'd also encourage people to look at the TESS archival data, the Kepler K2 data. I'm sure there's the TESS data is going to continue to deliver lots of surprises.
Thanks. We don't have any other questions, so we can move on.
Thank you, Eric. We really appreciate that.
Thank you very much. I wish I could see you all live, but
Yeah.
until next time.
All right.
Our next speaker will be Helena Ritchie, and she is talking about disk instabilities caused by the 2018 outburst of AG Draconis. Take it away, Helena.
Just get my screen shared here. Okay. Okay, so should be connected now. Could everyone see that okay?
Yes, looks good.
Okay, perfect. Okay, so hi, my name is Helena Ritchie. I'm going to be talking about a recent study that myself and my collaborators did on AG Draconis, and this was a paper that was published in the most recent publication of the JAAVSO. So just a background of what all I'm going to be talking about today. First, I'm going to be talking about my collaboration. So that's called Step Up. So I'll give you some background on that. And I'll also give you just a general background on AG Draconis as a system. And then I'm going to talk about our observation and data analysis. And in particular, I'm going to be talking about a tool that myself and my team developed that's useful for extracting light curves from photometric data. And then I'll talk about our results. So this is where we are. So just again, some background about me. I'm a graduate student from the University of Pittsburgh in the Department of Physics and Astronomy. And I also did my undergrad at Pitt. So during that time, I was the lead of this group known as Step Up. And I was the lead of this group for 3 years. And what Step Up is, it's an acronym. It stands for the Survey of Transiting Extrasolar Planets, the University of Pittsburgh. So we are actually an undergrad group that has like faculty advisors and stuff based out of the University of Pittsburgh. And we have access to this observatory called the Allegheny Observatory, which is located about 10 or 15 minutes away from Pitt's campus. And through the observatory, we have access to this telescope called the Keeler Telescope. And it's a Meade RCX 400. It has a different CCD now, but at the CCD that was used to collect this data was, you know what, I can't remember the specs off the top of my head, but it had about a 20 by 30 arc minute field of view. And you could see also on the top of this instrument, there's a little astrograph mounted there. And you might wonder, you know, Pittsburgh, that's in the Northeast, it's cloudy and rainy there all the time. Why would anyone put an observatory there? It's also right next to the city of Pittsburgh and has tons of light pollution. You could even see kind of the gradient here on the sky facing towards the city. So this is a historical observatory, but so that's why it's in Pittsburgh. It was there before the light pollution was really an issue. But actually now we are still able to do some pretty effective astronomy from this site. So these images were taken with that astrograph that I pointed out that was mounted on top of the 16-inch. And so these are taken by my colleague, and this is the Andromeda Galaxy, and this is the Orion Nebula. So very beautiful images. So, you know, it just goes to show that you could definitely do astronomy near a city, especially if it's differential photometry, which is what I'll be talking about today. So like I said, Step Up is an exoplanet group, but we don't just observe exoplanets clearly by the title of this talk. We also observe, you know, through JAAVSO or through AAVSO for variable stars, because we were really just interested in making all the use of the telescope time that we have, because we have, you know, all the time really we could want on this telescope. So that's what led us to getting these observations that resulted in this publication. And we came across this, you know, this particular system because we were looking for a target that was circumpolar, that we could observe in the Northern Hemisphere from any point during the year. And there were observing campaigns for this system because it was outbursting kind of as we were looking to put our telescope time to use. So that's what resulted in us collecting this data. So now I'll talk a little bit about some background on AG Draconis. So this is a symbiotic binary system. It contains a white dwarf and a red giant. The red giant in the system is underfilling its roche lobe, but still losing mass that's accreting onto the white dwarf. And it was recently discovered that there is an accretion disk in this system, which is important for this study because we determined that disk instabilities were the cause of this outburst. So this is kind of a unique system as far as symbiotics go, because we have a really extensive observational history of the system. This dates back like 100 years, even longer than that, I believe. And this study that this figure is from, a lot of this data is AAVSO International Database data. So it's unique because we can see there's a lot of different sizes and recurrence times of outbursts, but they're fairly predictable in the sense that they have a recurrence time of roughly every 10 years or so. We'll see an active period of this system. So it's nice to be able to observe these phase transitions and use that to try to tell us what's going on with the outburst mechanisms. So when we observed the 2018 outburst of this system, we were really interested in using the shape and the scale of the outburst and its color evolution to tell us about what could have caused this outburst. So now I'm going to talk about the data we collected and how we did our analysis. So these are the light curves. They include all of the data that we collected over, I think, around a 3-month period or something along those lines. And you can kind of think of them as limits on brightening timescales for the system. And what we used to get those light curves was the tool that I mentioned a while back, known as step-up image analysis. So this is, I'm going to do a little plug here. So this is a Python tool that I developed whenever I first took over as lead of this group back in the summer of 2017. And its baseline purpose is to be an easy tool to extract light curves from astronomical image data. So essentially, it just takes files in the FITS format and does instrument signature removal, astrometric calibrations, and differential photometry, and spits out some of these figures. This is just an example from older data that we had of a transit of the planet WASP-52b. So there's a lot more information about this tool on SIA's GitHub. If anyone is interested, I'm happy to answer questions about that. And we have a lot of really great, I'm not a computer science student, but we do have some newer members of Step Up that have done and made a lot of really great improvements on this pipeline recently. So I'm very excited about it. Okay, so now we can talk about our results. So this is pretty much the key figure of the paper. It shows the outburst in different filters. So this is the R band and this is the V band. This is all AAVSO International Database data, and we have our contributions overlaid there. So this outburst occurred within about a year following its previous outburst and at rather small amplitudes. So that was our first piece of evidence that led us to believe that this was of disk instability nature, because with something like a thermonuclear runaway or different mechanism like that, we're typically seeing larger outburst amplitudes and larger recurrence times. That was one thing that was suggestive of a disk instability outburst. And another, we use this data to do analysis of the color evolution. So that's what this figure is down here. This is showing the V-R color. And you can see that leading up to the peak of the event, we're seeing a slight increase in overall temperature of the system. Keep in mind, this is unresolved data because in the sense that it contains light from the disk, the white dwarf, and the red giant. But still, we are seeing an overall increase in temperature of the system, which is what happens in the disk instability, and then kind of an exponential drop off here in temperature overall of the system, which this shape of cooling times here corresponds to how material propagates through an accretion disk. So this evidence combined is what led us to our conclusion. It is important to note that, again, this is unresolved data, and we would need further data resolving the individual components of the system to really make this conclusion. But the combined pieces of evidence here are a pretty convincing argument that disk instabilities cause this outburst. So that is all I really had to say. I just want to take a minute to thank the StepUp observers who helped to collect this data, and StepUp's mentor, Michael Advasi, and the Allegheny Observatory manager, Lou Coban, and of course the AAVSO AID contributions, because this simply wouldn't have been possible at all without that data, and to the meeting organizers and JAVSO editorial staff. Thank you.
Awesome. Thank you, Helena. It's great. That was very interesting talk. Do we have any questions?
We haven't got any, so people, come on.
While people are typing their questions, this is Elizabeth at headquarters again. Helena, your talk was great, and I really enjoyed working on your paper for the Journal of the AAVSO. Congratulations for publishing there.
Oh, thank you. Thank you for all your help.
Well, you're very welcome. I wanted to mention too that AG Draconis is another star for which there's an ongoing AAVSO observing campaign. Jaroslav Merk and Rudolf Gale from Slovakia have had a campaign running since the outburst in 2018. And so we'll put the alert notice link in the question and answer box so you can see it. It's alert notice 631.
Okay, we have a question. Have you transformed your data?
What was that?
If you transformed your data.
Transformed.
If you apply transformations to your photometry.
I'm not exactly sure what you mean by transformation.
Actually, you collected data from the AID, so you didn't apply any transformation. I think you just used the data as it was.
Right. Yeah. Oh, so okay. So looking at this light curve, this isn't necessarily a transformation, but this isn't just like the straight raw data off of AID, because we did put this into bins of, I think, around like a third or like 1 day in this light curve, and in this light curve we bin them by 0.3 days because we wanted to make sure we could get the resolution to see this event. And also you'll notice that there are different colored points here. So the ones that we considered in our analysis, the blue ones, those were high signal to noise data, because whenever we were subtracting them to get the color light curve, noise was introduced that kind of drowned out the signal. So that's kind of how we did the analysis of the AID data. So we did manipulate it a little bit.
Yeah. Well, there is another question from Greg. Is your code available? And if so, what is the link to it?
Yeah, this code is available. So this is the GitHub repository that you're seeing on my screen here. So if you just go to GitHub and search this repository, you should be able to find it. So yeah, it's publicly available on GitHub. It has an install script that was recently developed that seems to be working pretty well. So, and I'm also very happy to, answer any questions that new users may have if they're trying to get this installed. One
comment from Bob Bookheim. He says, there is a pretty large set of spectra of AG drag on the ARAS database, plus a dozen or so in the AV spec. Thanks, Bob. I think that's it.
Okay. All right. Well, thank you again, Helena. We appreciate that. That was a great talk. And I guess we're ready for our next speaker, Madelyn Madsen, who is going to speak about simultaneous photometry on VSX variables and TESS exoplanet candidates. Take it away. Are you able to unmute yourself? Does that work?
There we go.
Good.
Hello. Go ahead and share my screen here. you guys able to see that?
Yes, we are.
Okay. All right, hi, my name is Madelyn Madsen. I am a undergraduate student here at Minnesota State University, Moorhead, and I am doing research under Dr. Matt Craig. And I did some research over the summer, which I will be presenting today. So I did simultaneous photometry on the VSX variables and TESS exoplanet candidates. Oh, I'm here, there we go. So this right here is an image that we observed this summer, June 27th. And you can see here the apertures in the field. So we're looking at a TESS target. And on the right side, you can see in the center, there is T1. That is the target that we are aiming to observe for this night. And around it, you can see the green are the TESS targets. The red are comparison stars and blue are variable stars. If you have trouble with the color, the TESS targets have a T label, comparison stars have a C label, and the variable stars have the V label on there. As you can see in this field, the variable star V11 was originally labeled as an APAS comparison star, but we detected fluctuations in the field in this night, so we relabeled it as a variable star in this night. Oh, I have some text slides, but I'm going to be going past those. If you're viewing this just as a PDF, you can look at those. So with our software, we were able to get a seeing profile for this night, and we found that the full width half max is 5.96 for this target on this night. And these observations were done with a RP filter. So we can see this here is our light curve. And what we're trying to find here is the transit of the exoplanet as it passes in front of the star that we're viewing. So on this, well, on all three of these lines, but on the top line here, you can see that there is a dip where we see that the exoplanet is transiting in front of the star, and then it comes back up once the planet exits the transit, or exits the being in front of the star, and it returns to its normal magnitude. Right here, we're seeing the flux of the star. So it's not just the raw data. We compare it to all of the comparison stars in our field to get a normalized flux, which is the blue. And then for this night, we detrended the data with air mass and the for this one, it was just air mass, sorry. And on the bottom here, you can see this assortment of plots is the calibration data from the night. So things like air mass, sky per pixel, the X and Y position of the star in the field, and other things like that. So for this night, we only saw an egress, but we were able to view it, and we saw it translated a little bit to the right from the expected egress. Moving on. So on August 6th, this year as well, we observed the same field. So we're observing the same star, but this time we are observing it in two filters, a B filter and RP filter, to check the chromaticity of the star. So on the left, we have the B filter, the right is RP, and again, the same color and labeling system applies for this field as well. So we have the seeing profile for both filters here. We can tell that there is clearly more noise in the B data. It's clearly not quite as smooth of a curve as the RP, but we did find that the full width half max is 6.6 for the B filter and 5.36 for the RP. So here we have the light curves for both filters. You can see that there is a gap in the data in both filters, and that is because there was a malfunction with our computer controlling the telescope and the camera, and so we missed a portion of the light curve. But luckily, it was in the middle of the transit, so we were still able to get the ingress and egress, so we could still plot a model. So it worked out all right. And again, we have the blue up top is the relative flux, the normalized relative flux, and then the red and the green are detrended. This one is detrended with air mass and then also the X position of the star in the field. And then the green just being the transit model as well. So this night, the August 6th night, as well as the June 27th night, we were actually able to submit 2 tests and to the follow-up group. And we have since done another submission. So we are able to do observations and analysis to get our data submitted to TESS just this summer. So that's really exciting. And also with our data, we are able to observe variable stars as well. So we do photometry on all of the stars in the field, and that includes any variable stars that we have. And so this light curve here is from a variable star in both nights. So this is the one labeled V12 in the aperture fields from before. And this is the name is up there, but I'll just let you read that. It's a bit long. And this variable is a variable type EW. So they're eclipsers with nearly identical masses and temperatures, which makes it very difficult to specify the ends of the eclipses. Okay, right. And so we have here the left-hand side is the first night, our June 27th night, and then the right-hand side is our second night, the August 6th night. And you can tell that because we again have the gap between or in the middle of the August 6th night. And here we have them laid over each other. So I guess that's a little difficult if the colors are tricky for you, but the first night is in blue, the second night is in green, and then in orange we have a difference between the variable star that we were observing and a comparison star in the field, because we had we found in a comparison star that there was a dip similar to the beginning of night 1. You see this dip down below that goes up and then back down. And we found that same dip in another comparison star. So that tells us that that change in brightness there was not actually from the star, but rather just atmospheric data from that night. So we subtracted that out, and then you can see that the green and the yellow fit much nicer in there. And we plan to do more analysis on this variable star and submit some data to the AAVSO once that happens. So if you are interested in viewing or using or viewing any of our software, you can use this QR code and it'll bring you to our GitHub repository for our software. Any questions?
It's great, Madeline. Thank you. We look forward to getting your data in our database.
Yes, we have a question from Gian Bruno de Sierras. He asks, what's the RP filter?
Right, so in our observatory, we have a few different filters that we can use to take pictures, and the RP is our red filter. So when we were doing the red or the RP and the B, it was our red and blue filter. So when we're looking when we're using the RP filter, we're looking at the red light in the stars.
So they are not actually standard RC filters, they are just red filters, not standard bands.
Yeah, I'm not quite sure about the specific specs of them.
And we have another question, a technical question by Gabriel Negu. He asks how to convert fluxes to magnitudes in AIG. I don't know if you know that, but. Yes.
Oh, in AIJ?
NIJ, yes.
Right. So for TESS, they tell you to use the AstroImageJ software, but for our analysis, we actually don't use AstroImageJ. We're using AstroPi, and our transits are with the Batman transit module. So we're not using AIJ, although we are making our plots, manipulating our plots to have the same kind of output look as AIJ to be consistent with the other TESS submissions.
Okay, thanks. And we have two questions from Bert. He asked, how do you create the model for the transit? What parameters do you use?
So we're using the Batman transit module, and the parameters, we can change the parameters based on different things, but we do use things that you can find in like the ExoFop or the TESS transit finder, the depth of the transit or the predicted depth of the transit, the period, the like ingress and egress, stuff like that, the midpoint of the transit. So we fit different things based on the night to get a more accurate transit.
Finally, is the software still called Glowing Waffles, or have you updated that?
It is not, it's no longer called Glowing Waffles. Now it is called Stellar Photo. And you can find that all on the GitHub repository. So Stellar Photo now.
Oh, I like Glowing Waffles.
I did too, it was good.
Anyway, thank you again, Madeline. We really appreciate this. The next presentation is going to be by our very own Lindsay Ward, who is going to talk about the AAVSO Ambassadors Superstars.
Hi, this presentation is not something given by me. It's actually a video that's going to be played about our ambassadors made. AAVSO ambassadors are undergraduate students, graduate students, and young professionals who compile really great educational content on any astronomy that they find interesting to them, and they put it out to the public. They are involved in online star parties, and they promote the AAVSO, and so please join us to view this video that they created. I call them superstars, so I titled the video AAVSO Ambassadors Superstars, their niches, their contributions, and their why.
Are you seeing it?
Yep.
Hi, my name is Heather, and I am an ambassador and volunteer with the American Association Observers, also known as the AAVSO.
Hi, my name is Anna Para, and I'm an ambassador for the American Associate of Variable Star Observers.
Greetings, Sky people. My name is Molly Wakeling. You might also know me as Astronomolly, or by observer code WMOB on AAVSO.
Hi, everyone. My name is Skylar Larson, and I'm an AAVSO ambassador.
My appetite to explore the universe emerged after binge watching Cosmos Space-Time Odyssey in my mid-20s. And soon after that, I enrolled in my local community college and took a course called Astronomy 101. And after completing that class, that's when I realized I had a big passion for astronomy.
I'm a PhD student at University of California, Berkeley, working on my doctorate in physics. And I've been doing astrophotography for about the last 5 years. And it's been just a real joy. Absolutely love doing it, and I'll probably never get tired of it. There's so many different things to do. After doing traditional astrophotography for the last several years, I've been wanting to get into scientific data taking, and I recently joined the AAVSO, and I finally got a rig put together of various bits and pieces to be able to take scientific data for the AAVSO and also for NASA's Exoplanet Watch program.
I am a beginner amateur astronomer. I'm interested in learning as much as I possibly can about our universe. And I'm here making this video as a member of the AAVSO Ambassador Leadership Team to explain to you what a variable star is. So what is a variable star? When a star, as observed from Earth or any observing point, starts to or has been behaving strangely over time, the first thing we notice is the star's brightness begins to fluctuate. The luminosity of that star is varying. The change in the emitted light can be caused by some pretty neat things. It could be a star swelling or shrinking, getting ready to explode its contents across the cosmos. We call that an intrinsic variable. Or there may be something partly blocking that light. It could be a cloud of dust or even an exoplanet. And causing an eclipse in front of that star. And we call that an extrinsic variable. Even our own sun, that thing over there is a variable star. Its luminosity varies about 0.1% over its 11-year cycle. That's pretty cool. How do we measure a star's brightness changing? Well, by constantly observing it and documenting the magnitude. The apparent magnitude is what the star's brightness is. There's a scale there. Some stars vary over long periods of time and some really short. The data is used to monitor and predict what might be happening with that star. And if something really exciting is going on, the star will get a bunch of attention. Kind of like Betelgeuse recently, the second brightest star in Orion. It started to dim and do some pretty weird wobbly stuff into late 2019. But it has regained its brightness. We're still not 100% sure what caused that dimming, but there's been a few studies saying it's probably a cloud of gas, but I'm gonna let the experts look into that one.
Where do you even start? I started very early. I was a toddler when I started just stargazing with naked eye in my backyard, going to libraries to get all the books that I could possibly find on the subject, just researching about it on my own. And in high school, I was lucky enough to have the Boys Astro organization visit my school and teach a seminar about publishing a paper. Find your local astronomy community. There's bound to be a group of people in your area that study astronomy. Just get in touch. Nowadays, I am an AAVSO ambassador specifically for outreach and education. I make my own videos on astronomy topics that I like. As an MIT undergrad, I research centaurs right now. Centaurs are these little green dots, and they're like asteroid comet-like things. I'm trying to find satellites around them. But how exactly do I do that? Well, if you can't afford a telescope like I can't, I mostly specialize in data analysis. That's kind of taking images or data from a database that like somebody's already taken and kind of chugging it through some code and basically finding patterns in data. You can do this in a lot of ways. You can find light curves with variable stars. You can find light curves with exoplanet transits. You can try to find satellites going around solar system bodies, kind of like I am. There are loads of ways to contribute to data analysis in astronomy.
At the end of the Astronomy 101 course, my astronomy professor offered me a spot in her team to study binary stars, which I happily accepted. Binary stars are two or more stars orbiting a common center of mass. My research experience was very rewarding because I got to strengthen my research skills, I'd made new friends, and I was one baby step closer to understanding the universe. After completing my binary star project, I was able to jump onto a new research opportunity that focused on exoplanets, planets that exist outside our solar system. With the support of the AAVSO, I was able to join a team that focused on exoplanet transits using a transit modeling software called AstroImageJ. My curiosity on exoplanets grew, and I found myself on NASA's website trying to answer some very important questions about exoplanets.
I'm going to show you my telescope setup and talk a bit about why I got into astrophotography and how I got into scientific data taking. So I'll give you a little tour of what I've got here in my backyard in the East Bay area of California. This is the science rig, which is the one I take my AAVSO and Exoplanet Watch data with. This is a Celestron CGE Pro that is mostly functional. It's unable to guide at this moment, but the nice thing with doing variable star observing is you don't need the best guiding, you don't need the roundest stars, just round enough to be able to register them. On top here is a 8-inch Vixen Newtonian f4 telescope, 800 millimeter focal length. I have an old Orion Starshoot Deep Space Monochrome Imager 2. I have a Starlight Express filter wheel that I have loaded with photometric filters, which is, you don't need to do photometry with AAVSO, but it's a type of observation that they like to get if you have those filters. And I have a RoboFocus focuser that I took off one of my other telescopes and attached to here, and it's been working quite nicely. One of the interesting things about doing variable star or exoplanet observing is that you don't actually need as kind of gear or as precision of tracking as you need for doing deep sky astrophotography. A lot of times the exposures are only 30 seconds, 1 minute, 2 minutes, not usually very long exposures like I would do for my deep sky. These stars don't have to be as round, and you want nice round stars for getting nice looking astrophotography, but for data taking, the stars can be slightly elongated, have odd shapes, things like that. The only thing that really matters is that the exposure is not overdone and that they're round enough stars to be able to register and align. So the requirements for doing variable star data taking is actually much less than doing astrophotography, which surprises a lot of people. The cool thing about taking variable star observations, either on your camera or even visual, if you're more of a visual observer, is that data that you take on the magnitude of that star on that given night, you can upload to the AAVSO website, and that gets collected into a database, and researchers can use that data in their research papers, and you can get cited in the papers, and it's a really great resource for the scientific community. You can contribute to the science doing, because on these bigger telescopes they don't have the spare time to be taking data, but I've got all the telescope time I want. I don't have to dedicate it to other things. I run this thing doing variable star targets all night long, every night that it's clear. So you can contribute to a wide variety of science right from your own backyard. And if you're an astrophotographer, you can do it with equipment that you already have. It can be really rewarding to see your data show up on the light curve generator on the AAVSO website, and getting the emails that say that my data was downloaded as part of a data set that a researcher was using. It's a real joy to be able to know that the images that I've taken on the amateur side of the house are also being used for science, in addition to the research I actually do for my PhD.
If you want to know more about the organization and what our members love about this aspect of astronomy, or get involved with the Ambassador Program, please check out the website, www.aavso.org, and see what we're up to. Thanks.
Being a part of AAVSO has been a lot of fun for me. And I look forward to being able to share what I've learned about exoplanets to others and meeting folks who are curious about astronomy. So thank you for your time. Bye.
Clear skies.
This is a cool video.
So if anyone is interested in the Ambassador Program, please just email me, lward@aavso.org. Thank you so much. And up next, Sarah will introduce our next speaker.
Yep, thank you, Lindsay. I can see why you call them superstars. And our next speaker is probably someone many of you already know, Joyce Guzik, who's going to talk about search for variability in 30 bright metallic line stars observed by the TESS spacecraft. Go ahead, Joyce. You should be able to talk now, yeah.
Okay, I am trying to share my screen. Can you hear me?
We can hear you and we can see you, yep.
Okay, my screen is starting to come up here. Let me try to do slideshow view. Okay, can you see that okay?
Yep, perfect.
All right, good. Just have a problem with my bottom of my screen being covered, but I'll work with it. Okay, so thank you for the opportunity to present today. So I'm going to be talking about a project I'm doing using TESS spacecraft data. So I'm going to be focusing on two different types of variable stars today, the Delta Scuti and the Gamma Doradus variables that pulsate in many modes simultaneously, both radial and non-radial. And these stars are burning hydrogen into helium in their cores on the main sequence. The Delta Scuti stars are about 2 times the mass of the sun, and they pulsate in pressure or acoustic modes with periods of about 2 hours. The Gamma Dor stars are a little bit less massive, about 1.5 times the mass of the sun, and they pulsate in gravity modes, and they have longer periods of 1 to 3 days. So it's much more difficult from the ground to discover Gamma Dor stars and to get a full light curve because of their longer period. So on the right, you see a Hertzsprung-Russell diagram, luminosity versus effective temperature, and you see the solar-like stars in the yellow at the lower right, and the sun with the circle. So the Gamma Dor stars are just above that on the main sequence, about 1.5 times the sun's mass. And the Delta Scuti stars are a little bit higher than that along the main sequence in the blue circle. So these stars have different interior structures, and astroseismology has been a great tool to try to see inside the stars or determine their interior structure. The Delta Scuti stars, unlike the sun, have a radiative envelope and a convective core. So in this radiative envelope, photons from the interior are random walking their way out to the surface, scattering off of the electrons and ions until they reach the surface and then emerge as the light we see. The sun and the Gamma Dor stars, on the other hand, have convective envelopes. So convection rather than radiation is transporting the energy from the core. The outer layers are just churning, boiling, carrying the hot layers from the inside up to the surface. So why do Delta Scuti stars pulsate? Well, they're driven by this mechanism called the kappa effect, which is occurring in the region where the second electron of helium is ionized. So I have a little picture of a helium atom there with the 2 protons and the 2 neutrons and the 2 electrons. Well, the first electron comes off at higher in the atmosphere, but at about 50,000 degrees inside the envelope, the second electron is being ionized, and it forms a bump in this picture of opacity versus temperature. So the center of the star is toward this direction on the left and the surface is toward the right. So as radiation is trying to get out, these places of high opacity is where the radiation is impeded from getting out. So this is further inside the star. But out here at this He plus, or first helium ionization region, is where the Delta Scuti stars get their pulsations driven. These photons try to get out here, but instead of just scattering off the electrons, they knock an electron off of the helium atom, and they cause a higher pressure here, and then this region expands out. And then when that region cools, it comes back in again, and the electron recombines, and it's set up to get another push by the photons coming out. So this mechanism is called kappa because the symbol Greek letter kappa is in the equations of radiation transport and stellar structure for stars. So that's why it's called the kappa effect. So a little bit about the TESS satellite, the Transiting Exoplanet Survey Satellite. It was launched in April of 2018. Its main mission was to search for transiting exoplanets around nearby G, K, and M stars. But it can view any other kinds of stars as well. It's continuously viewing individual targets for 27 days, and if the star is near the pole of the ecliptic, it can see it for up to a year, as long as the spacecraft is pointing in that direction. So the TESS project has a guest investigator program to which we applied, and we asked for 2-minute cadence light curves. So we received light curves on a number of stars where one data point was taken every 2 minutes of integrating the light, and over 27 or more days. So that's really high cadence and long time series and high precision data that is almost impossible to get from a ground-based survey. So the TESS spacecraft so far has observed most of the sky both below and above the ecliptic plane during its first 2 years. In the first year, it looked at the southern sky below the ecliptic plane in these 13 strips. They're called sectors. So it moved every 27 days around the plane, around the sky in the southern sky, and then then after 1 year, it turned around and looked at the northern hemisphere during cycle 2, and it finished 13 strips around the northern hemisphere. So the data that I'm going to show you today is from cycle 2 from the northern sky above the ecliptic plane. And you see here, because these strips overlap near the ecliptic poles, these regions of the sky get observed for the full year. So the TESS investigator program that we proposed was to look at these metallic line A-type or AM stars, as they're called, and their pulsation driving. So AM stars show a significant underabundance of calcium and scandium and enhanced abundances of titanium and iron group elements. And these abundance anomalies, this is compared to the sun, these abundances are measured. The abundance anomalies are believed to be caused by radiative levitation, which is photons coming out and pushing the atoms upward in the atmosphere relative to hydrogen, and also by diffusive settling, by gravity and the thermal gradient causing the elements to settle relative to the background hydrogen. So some of these are susceptible to being pushed up, and some of these elements are falling down relative to the hydrogen background. And diffusive settling is also expected to cause helium to settle out of the pulsation driving region. Remember that helium plus bump that I showed you. And if it settles out of there, the Delta Scuti pulsations shouldn't be happening. So we expect these AM stars to not be pulsating in Delta Scuti modes. And my colleague, Catanzaro, used spectroscopy and Gaia parallaxes to determine stellar parameters and detailed abundances for 62 of these AM stars. So our goal was to use TESS to determine whether these stars are pulsating and eventually follow up, and if they are, find out why they're pulsating. So these are the stars characterized by Catanzaro on the Hertzsprung-Russell diagram. And you see these crosses are basically the uncertainties in temperature and luminosity that were obtained. And most of the stars are falling in the Delta Scuti instability region here between these two red dashed lines. Some of the stars are falling in this region between the Gamma Dor instability region here and the Delta Scuti region right here. So we would expect these possibly to pulsate in both Delta Scuti and Gamma Dor modes if they didn't have these peculiar abundances and possibly have the helium drained out of the envelope. And then there even are some AM stars in this sample that are hotter than the Delta Scuti instability region. So this picture really summarizes our results from our TESS Cycle 2 campaign. The TESS spacecraft looked at 30 of these AM stars during that year, during Cycle 2. And these lines show the blue edge and the red edge of the Delta Scuti instability strip. And these show the blue and red edge of the Gamma Dor instability strip. So we found out of these 30 stars, 2 Delta Scuti stars. They're labeled by these deltas right here. And they're in the Delta Scuti instability region, but because they're AM stars, we don't know why they're pulsating. We also find 2 Delta Scuti Gamma Dor hybrid candidates labeled with an H. Well, this one's right in the middle of the Delta Scuti instability strip and pretty far from Gamma Dor instability strip. So we have to understand why this one is showing low frequency Gamma Dor-like modes in addition to the Delta Scuti modes. This star is actually right in the Delta Scuti Gamma Dor hybrid region, so it's in the right place. In addition, we found 4 stars that had some low frequency modes that are Gamma Dor candidates. But these stars are way over here on the blue side or even beyond the Delta Scuti instability region. So they should not be over here. They should be over here. So we have to understand what's going on with them and are they really Gamma Dor stars? There was one eclipsing binary, surprisingly, in our sample, labeled with this B here. And this was previously known to be a binary with a Gamma Dor component. And I'll show you the light curve for that in a second. And then we had 12 stars with variability of unknown origin. They weren't constant, but they didn't look like they were pulsating in Gamma Dor or Delta Scuti type modes. And finally, what we expected to find were that all the stars would be constant, but instead we only found 9 constant stars that showed no photometric variability above 20 parts per million. So I'm going to show you just a couple examples of the light curves that we found. This is the TESS light curve for a Delta Scuti star, magnitude of about 8, effective temperature 7600 K. It was observed during sectors 25 and 26 at the end of Cycle 2. And a 3-day blow up of the light curve is shown here. You see there's lots of up and down over this 3-day, and the amplitude envelope is changing. And you can use a Fourier transform or technique to figure out what the frequency content of this light curve is. And this is a picture of this, and you see there are a whole lot of modes right over here between about 23 and 40 cycles per day. So less than an hour frequencies or periods. So this is definitely a multi-mode Delta Scuti pulsator. And some of the modes in here may not be the intrinsic frequencies but they may be combinations. So there's a lot of work that needs to be done to sort out the frequency content and eventually to model this star and determine more about the interior structure and also about why it is pulsating. And after last week's data mining workshop by Colin Littlefield, I was able to do a Fourier transform of this star myself. And here are the frequencies that I obtained after using light curve and V star on it. And you can see all the frequencies between 23 and 40 cycles per day. So I'm really pleased to be able to do some of this analysis myself instead of relying on my collaborators entirely. This is the Gamma Dor star in the eclipsing binary, showing these alternating eclipses. So this is sector 14 and 15. And this is a picture of the light curve blown up and folded. It wasn't folded exactly on the binary period, so you see this is drifting a little bit, but you can look at the 2 components more closely here. This eclipse here, the secondary, which is a 0.67 solar mass star, is totally eclipsed, and you can see it's flat on the bottom here. And this is the Gamma Dor component. It's 1.8 solar masses, and it's about 58 times brighter than the other component, and it's also larger. So it isn't totally eclipsed by this smaller star, but the eclipse is deeper because it's so much brighter. And finally, here's an example of one of those stars that have a light curve that needs more work to explain. This is a hot star, 8400K, magnitude a little bit less than 9, and it has this this light curve over 2 sectors, you see, with a pretty long period, few-day period, and this is a 3-day zoom in, and it's not really characteristic of a Gamma Dor or a Delta Scuti star. This was listed as a periodic variable of about 3 days. So this needs more explanation. Maybe it's a contact binary with a spot on it. Maybe it's a Gamma Dor pulsation. Maybe it's a single star with rotation and spots. So we have to do more work to understand this and observe it for longer. So in conclusion, these metallic line AM stars should not necessarily pulsate, but we did find 4 out of 30 that are showing Delta Scuti modes, and some that are even Gamma Dor candidates. We found many other stars with photometric variations that need follow-up to be explained. And this new test data on the binary with the Gamma Dor component will provide more constraints to model the Gamma Dor star. It's nice to find pulsating stars in binaries because then you get additional constraints on masses and the radii of the stars. Okay, thank you. Are there any questions?
That's great. Questions?
We don't have questions, but I will take this time to ask myself some questions. Make a comment on the last light curve of that weird star. I bet that this is an ACV variable. Yeah, an alpha Cannon Venaticorum variable. It's the typical light curve of those stars. They are called magnetic variables. Yes, so they are spots, but they are hot stars and not the typical dark spots. So I go for that. Yes.
Right. So what causes the spots if they're hot stars?
Magnetic fields, large magnetic fields. Yes. Mm-hmm. And if this is an A-type star, it's an A-type star. You said yes. It was hot. Yeah, it fits perfectly. Yes. So it's really that. And you talked about hybrids. I see that Delta Scutis and Gamma Dors have different masses. So those hybrids are supposed to have 1.5 solar masses, more or less intermediate masses.
Between 1.5 and 1.75. It depends. They should be right in between the typical Gamma Dor and the typical Delta Scuti. Those masses also depend on the metallicity. At the lower mass stars, if they have lower metallicity, can get into the Gamma Dor instability region. And as the metallicity goes up, the mass of the star that gets into the Gamma Dor region becomes larger. So it depends on both the metallicity and the mass, on whether they fall in the Gamma Dor region.
Great. We have a question. Perhaps you mentioned this, but do the same frequencies keep appearing in repeated observations of a periodic variable?
Yes, the same frequencies in a Delta Scuti star, are you referring to?
He doesn't mention it, but...
Yes, the same frequencies are very constant, at least over these time frames of 27 or 35 or several sectors. So 27 days up to a year, you do see the same periods and same frequencies and even the same amplitudes if it's a pulsating variable. There are some exceptions. The frequency content can change over many, many years. So if we look 10 years from now, you might see something different. And that would be one way to determine, as I learned yesterday, whether these are spots or something else, or pulsations. If they're changing over a fairly short period, they're probably spots that are changing over time. So again, more time and looking at them several years from now would be useful.
And that's when AAVSO observers are important, because they can provide us with long-term light curves. So keep doing.
And these are fairly bright, but some of these have fairly small amplitudes. So this one is 0.013 meg, and I guess we could look at this one with the AAVSO. The AAVSO observers could see this light curve. Yeah.
One last question. We have time for one last.
Yeah, one more.
What's the difference between pressure, acoustic, and gravity modes?
Well, pressure and acoustic modes are the same thing. They're sound waves. They're waves where the just like the sound we hear, there are longitudinal waves in the atmosphere that change the pressure of the atmosphere up and down, and that's what creates the sound that we hear. So these are a similar type of wave in the star is a pressure mode. The gravity modes, on the other hand, are more like waves on the ocean. Gravity pulls the material up and down. So, and those are longer period than the pressure waves. So different mechanism for causing the motion of the matter in the star.
Thanks.
Okay. There actually is one more question. Do you want to do Ray's?
If we have time, okay.
Right.
Is metallicity changing as in heavy elements landing on the star, or is hydrogen escaping to change the metallicity?
The metallicity, the star, we don't believe any of these stars are accreting any material or getting rid of any material. Rather, the elements are changing, are concentrating a little bit within the atmosphere. They're moving, some of the elements get pushed upward by radiation coming out from the star, and some of the elements don't experience that effect because their electron arrangement in the atom is different, and they actually sink relative to hydrogen because they're heavier than hydrogen. So it's all processes going on in the atmosphere of the star and the upper envelope of the star. There isn't any accretion or mass being lost in appreciable amounts in these stars.
Okay, thanks again, Joyce. We really appreciate your
Okay,
time.
thank you for the opportunity.
All right. Okay, our next talk is called The New Observations of SXV Star XX Cygni by Richard Berry, NolanSottoway, and Sol McCain. You guys should hopefully be able to unmute and start going.
Thank you, Sarah, and welcome to our friends, observers, and members of the AAVSO. I'd like to spend a moment to acquaint you with the basic facts of XX Cygni and our observing program. In years past, I have served as a mentor for the Pine Mountain Observatory Student Workshop. This year, the workshop was held as a virtual event. In years past, when we held the workshop on the mountain, it ran only 3 nights. As a result, the observing projects were basically demonstrations or exercises. This year, the virtual version of the workshop ran only 2 weeks, long enough to do some actual science. I chose this star because it is bright, has a short period, a large range of variation, and it passes directly overhead, so we could observe it all night long. And it offers some interesting but not earth-shattering science opportunities. The star XX Cygni is thought to be a monoperiodic type XXV variable with a slowly increasing period. However, there are scattered reports of early or late times of maximum in the literature. The historical record suggests the typical time of max errors are around 0.001 days, several minutes. Our goal is to obtain considerably more accurate timings by using a rapid image cadence and then fitting a polynomial to roughly 250 data points during near maximum. By relying on many points, we expected and obtained better timings. In the sample of 23 new times of maximum that we're reporting, we see no early or late times of maximum. Now I'll turn the story over to NolanSottoway.
Thank you, Richard. We took would you mind passing over control and pressing next slide?
Actually, I don't have that. Okay.
All right. We took our images using the Rowe-Ackerman-Schmidt astrograph at Alpaca Meadows Observatory. It was equipped with an 8 Horizon one-shot color CMOS camera. We used low gain mode, then 2x2 to make monochromatic images, and we shot at 10-second exposures. Subsequent testing showed us that our Bay Array images are reasonably close to V-band or TG photometry. We ran from dusk to dawn each night that the weather permitted, taking about 2,500 images a night. Next. And the animation as well. After each night of collected images, it was one of my rules to run them through the AIP for Windows magnitude measurement tool. I quickly learned to recognize the comp star, the check star, and the target star, XX Cygni, and I can't say I'll ever forget them, having seen thousands of these images pop up onto my screen. Next slide. AIP for Windows magnitude measurement tool produces a text file in the AAVSO extended file format. The file tabulates the heliocentric Julian date, measured magnitudes of the target and probable error, comp stars and their probable errors, the air mass, and so on. We imported this file from into Microsoft Excel or Google Sheets for analysis. Next. This is a typical peak in an XX Cygni light curve plotted in Excel. We show about 250 data points brighter than an instrumental magnitude of 11.8. It is plotted here with error bars. Typically 28 thousandths of a magnitude. The red curve is the best fitting sixth order polynomial. It was then, by strong arming Excel to display the coefficients to 16 decimal places, that we were able to determine the time of maximum analytically. Next. Initially, we used a quick and dirty graphic process to obtain times of maximum. It would go something like this. We'd find the maximum, we can eyeball that and say it's where the red line is. We'll look to a point slightly to the left. Then we look for a point that is equidistant to the right, and we average those out. And that would give us our time maximum. However, as the name suggests, this is not a perfect process, and it is in fact quick and dirty. So to improve this process, I'm currently working on an analytic method using the R programming language to determine the best fitting polynomial, subtract it from the raw data, iteratively exclude outliers, and return the time of maximum light and peak magnitude. Next. Finally, we lumped all of our light curve data together in the AAVSO's V-star software to generate a well-defined light curve. This plot includes the entirety of our data, including noisy data taken in the evening and morning twilight, through passing clouds, and in differing states of focus. The plot contains well over 20,000 data points. Now I'll kick it over to my partner, Sol McClain.
Thank you so much, Nolan. If you could. In the 116 years since its variability was discovered, many astronomers have measured XX Cygni's time of maximum. Harlow Shapley, the famous Harvard astronomer, was among the first in 1911. For a time, the O-C curve has suggested an abrupt period change until around 1980. The consensus now is of a continuous change to a shorter period. For our presentation, I've brought the curve up from Blake's research in 2003, adding Yang's 2012 data, as well as our own. Next slide. Here are the times of maximum on an increasing time scale using the same O-C span of plus or minus 0.005 days, or plus or minus 7.2 minutes. This plot shows our data spanning 40 days. The standard deviation of our data, assuming a constant period, is 0.00024 days, or only 22 seconds. Next slide. We're looking at an 18-year time span of the exact same O-C scale as the previous slide. This data includes the Pine Mountain data from 2009 and 2020, a few points from Barry in 2010 and 2015, and 50 AAVSO data points provided by Jerry Samolek. The change here is unmistakable from the historical data to our own. To wrap up the graph portion, here is the 116-year-old data set using the quadratic ephemeris. This ephemeris is consistent with a continuously lengthening period, so that over time, the observed times of maximum fall a bit late. Next slide. In conclusion, this year's 2-week Pine Mountain Observatory virtual student workshop provided just enough time to carry out a project of scientific value. Not only did we add new times of maximum light to the record, but we successfully tested high cadence imaging, and we measured the resulting data using polynomial curve fitting. Our results appear to be more consistent and more accurate than commonly used methods. Finally, we find no support for advanced or delayed times of maximum light in our data. Next slide. We'd like to thank those who helped make this year's Pine Mountain Virtual Student Workshop a success despite the unusual circumstances. We'll now be happy to take questions from our listeners. Thank you so much.
Thank you all. Questions?
We don't have questions up to now. We have one from Horace Smith. Is there any evidence for long-term changes in amplitude?
Does anyone want to take this one?
We haven't analyzed the data yet for amplitude, but when Nolan gets our program working, we should be able to get amplitude from our data set. I have not seen evidence or checking for changes in amplitude in the papers that have been published about this star.
Okay, we have another one. This is not for Richard. Where would you like to take your astronomical research yet?
Sorry, I missed the end of that.
Where would you like to take your astronomical research? This is not for you, Richard.
I'll start. At this point, I'm just going to continue us writing the papers on this project, but I'm not entirely sure where it'll take me in the future. I'm looking forward to finding out.
Good answer. I am a freshman in college at the moment. It is a physics major, and I would love to continue with astronomy in physics if the interest pursues. Yeah.
Okay, we have another one from Gabriel. Has the temperature change been analyzed? If there is any, what does it show?
I have an answer for this, but Richard, if you want to take it.
Oh, go ahead.
I'm pretty sure we did not analyze the temperature, but we also didn't notice any particular changes in temperature over the course of the papers that we read, and the times that we didn't take temperature. We did some readings of color. It's a vague answer. You could probably do better.
Yeah, back in, I think it was 2009, I took a whole series of, I think, 10 sets of data in 3 or 4 Johnson color bands. And those definitely show the changing temperature of the pulsating star. That data hasn't been analyzed yet, but we do have it, and it will be part of putting together a complete paper when we do that.
Thanks. We also got several messages with congratulations for your work. I think we're finished.
Okay.
Thank you.
And I'll add to that. Yeah, our new council member, John Briggs, just said, great job. Keep it up. We'll all echo that. Thank you. Thank you all.
Thank you.
Okay, so for our next talk, we have, and this is the last one before the break, Types of Period Changes of W. Virginis Stars by Pradip, Karmakar, Horace Smith, and Wayne Osborn. Now, I can't find, is Wayne around? I don't see him in the attendees list. So
I don't think he will be joining us today.
Okay.
Hello.
Yep.
My sound is clear to you?
Yes, we can hear you.
Okay, okay. So can I start my sharing slides?
Absolutely. Go ahead.
Okay. Hello.
Yep, it looks good.
Is it clear to you?
Yes, we can see your slide.
Okay, so let us start. Okay, my name is Pradip Karmakar, an AAVSO member from India since 2018. And Horace Smith, Cygni Osborn are our collaborators. And Horace Smith is co-partner of today's talk with me. Today, we'll give a talk on types of period changes of W Virginis stars. This is the period luminosity diagram of Cepheids. Cepheids basically are of two types, classical Cepheids and type 2 Cepheids. Classical Cepheids are much brighter than type 2 Cepheids. In the diagram, the filled blue squares represent the W Virginis stars, and they belong to type 2 Cepheids. If we see the horizontal axis, then we can say that the period ranges of W Virginis star ranges from 4 days to 20 days approximately. And we have collected these images from OGLA data archive. Now, what about of W Virginis stars evolution? What does the theory says about the evolution of W Virginis stars? There are several models exist which are contradict each other. Some model says that W Virginis stars are evolved in the blue loops into the instability strip from the asymptotic red giant branch, and thermal pulses are the cause of this creation of the blue loops. But some recent models says that this type of blue loops do not exist, and they said the reason behind it that the thermal pulsation are too weak to create this type of blue loops. So we have the question now, blue loops or no blue loops? If we in favor of the blue loops, then we can see from this diagram that W Virginis stars evolves through blue loops formation into the instability strip from the asymptotic red giant branch due to the thermal pulsation. And we have collected this figure from work of John Persis in the year 2007. If these blue loops models are right, then we should see some W Virginis stars with period increases and some with period decreases. And we should also mention that the size of the period changes should be consistent with the time scale of these blue loops. We have said earlier that the evolution of W Virginis stars is still an unsolved problem, but the period changes of W Virginis stars have the potential to give some insight about the evolution of this type of stars. To study the period changes, we should need new and old data spanning long time intervals. In this slide, we have collected two images. The left-hand side images have been collected from a paper of Clement et al. Published in the year 1985. And this is the phased light curve of V2 in M10 with period 18.7226 days. And in this figure, we have used the old data set. And on the right-hand side, this is also the phased light curve of V2 in M10. And in this case, we have collected the recent dataset from SSSN archive. And we have also deduced the period for these SSSN datasets using the period 04 software. And we found the value as 18.70 days. And we have also cross-checked the period using the Piranso software. Now, how period changes can be defined using the O-C diagram or phase shift diagram. Here we have represented two O-C diagrams. These O-C diagrams are not those of actual stars, but are merely reminders of how period changes alter O-C diagrams. O-C results can be given in days or in phase units, that is, fraction of a period. In the figure, the upper parabola represents the continuously decreasing period trend, and the lower parabola represents an abrupt period increase trend. On the vertical axis, we have O-C in days unit. O represents the observed time of maximum of light, and C represents the calculated time of maximum of light. Now, this is the phase shift diagram of V2 in M10. If we see the diagram carefully, then we can see that here initially we have used double point just before 1920, as we are not well confirmed what was the starting point. And from this diagram, it is also clear that the period of the star V2 is gradually decreasing. So we can say that V2 in M10 shows a long-term decrease in period. And now this is the phase shift diagram of V3 in M10. If we see the diagram carefully, then we can say that the period for the case of V3 is gradually increasing, but in small amount. So we can conclude that V3 in M10 shows a small period increase. This is not the phase shift diagram nor the O-C diagram. This is the period shift diagram of V1 in M12. And we have collected these images from our published paper in the Journal of AAVSO in the year 2019. If we see this diagram carefully, we can say that sometimes the period of V1 increases and sometimes period of V1 decreases. So we can say that in this case, we have irregular period changes. And from this type of irregular period changes, it is quite hard to determine the long-term trend of period changes. Now, this is our final slide. W Virginis star period changes observation versus theory. Some stars with long-term continuous period changes are at least consistent with the blue loops model, but erratic period changes require some short-term source of period noise, as we have seen in the case of V1 in M12. And finally, we need long-term studies of more W Virginis stars to get some more knowledge about this star. Thanks to all of you.
Thank you. I'd like to ask you about those period changes. What are the most common ones, the abrupt ones or the continuous period changes?
I would like to prefer to answer Horace Smith.
Horace, unmute yourself. Horace, you have to unmute yourself. Can you do it? Yeah, that's
there,
it.
now it did.
Yeah.
It's a difficult question to answer, partly because of gaps in the observational record. We have good coverage for many of these stars in some years, but when we're going back to 1920, 1900, and there are gaps in the record and we see a difference between new and old observations, it's not entirely sure what's going on. So one of the things to do now is to make sure we no longer have any gaps in the data and that the observations of these stars stay more or less continuous into the future. That'll make answering that question much easier.
Yes, so more data needed. I have a lot of observations of Kappa Pav, the brightest one, and it has a lot of abrupt period changes. So it's very interesting. It's very bright, so we encourage people to observe it. We have another question. What does O minus C mean?
O means the observed maximum of light, and C represents the calculated time of maxima of light, and for this purpose we should use the light element, and to deduce the light element we choose an initial time of maxima, which is generally represented by T0. We can choose this as the previous time or present time. And second one is we have to choose an estimated period.
Thanks. We have another one. Can you discuss the statistical significance of the random period changes? How do you distinguish between random period change versus measurement uncertainty in the individual O minus C points?
I would like to refer this question to Horace.
Yes, that was that also, in some cases where there are not a lot of observations, is a difficult question to answer. If you do have a lot of data points, however, and we do for some epochs, for example, on V1 and M12, then you can determine through various programs, such as a Fourier fit or a least string size program, estimates of the period over a particular year or 2 or 3 year span that do produce error bars. And one can see whether those error bars show the period changes to be real. You can also plot the periods for different epochs with the different periods and see how messy the light curve gets. And some of those irregular period changes are certainly real, but it can only be determined sometimes when there are a lot of data points. So certainly another encouragement to keep observing these stars and get a lot of data points over a few years span to pin down what the period is over a few year time span. And then that will make the comparison easier.
Thanks, Horace. We have a comment from John Percy. He says that he's presenting a poster on a W Virginis star. Are you come? So Sarah has posted the link for you to go to.
That's a very interesting star, indeed.
Yep, that's a, please do go see the posters. Do we have the link for the general? I can put that.
Check the chat window and you will have that.
Here. I'll put them in the chat window as well. Any other questions for our speakers?
That was the last one.
Okay, well, thank you two very much. I appreciate that.
Thank you. Thank you, Horace.
Thank you all speakers. Now we have the break. I am going to share my screen. Lindsay, do you want to jump in?
If you want me to, sure. So we now have a break on. After the break, unless you're joining the Eclipsing Binaries breakout session, you will not be coming back to this link. You'll be going to www.aavso.org/links. And that will take you to all the links for all the other observing section breakout sessions. If you have any questions about how to get there and you're not sure after going to the aavso.org/links, feel free to email me. aavso@aavso.org is the general email address, and we'll be monitoring that account. So we'll be sure to get your email and help you get to where you want to be.
And remember that with these breakout sessions, these are Zoom meetings, they're informal. It's your chance to ask lots of questions about the sections, about that kind of stars. And everybody should unmute and talk and enjoy each other's company. So
Yes.
once again, thank you so much for attending this session.
Don't be
And thank you
shy.
to,
Don't be shy. Show yourself in the session.
yes, and thank you so much to our sponsors, QHY-CCD, OBSTech, Optical Structures, First Light Observatory Systems, iTelescope. They're very important to us as a nonprofit, and we sincerely appreciate all their support.
Absolutely.
All right, everyone can go enjoy their break, and then we hope to see you all in the sessions.
In about,
to hear anything you have to say and any questions, happy to answer them.
About 15 minutes from now, right?
Yep, so starting at 20 after the hour.
Right. Okay.
See you there. Bye.
Bye.
Someone's asking if they can share if we can share the links for the breakout sessions and how to get there. Yeah. www.so.org/links.
There.
Paste that into the queue as well.
I have this on a slideshow, so it changes. Okay. All right.
I just posted the links to the chat just in case someone gets lost.
Right. All right, and now going to promote Jerry.
There, you're live.
Yes, so anyone who stays in this session for the Eclipsing Binaries breakout, they are going to be promoted to a panelist. Since we're ending the meeting in the sessions, they can all be promoted to panelists, and that gives them audio, that gives them video.
Right.
But we'll give everyone a few minutes to end up where they want to be.
So should I go ahead and make Jerry the host now?
Yep.
Sure.
All right.
Then you don't have to think about it. Then it's done.
Hi, Jerry. You got all the power now.
He might be on his break too.
Yeah.
But you can take
He is not there. He'll see his notification.
Okay, I just got unmuted. Do you hear me now?
Yep.
Yes.
I'm trying to figure out how to get your video up. Unless you can.
I'm asking him to start his video. And by asking, I mean, whenever I say I'm asking someone, it means that they're getting a notification on their screen from me.
Okay. There you go.
Hello, Jerry. How are you today?
Oh, hanging in there.
Good.
Hi, Jerry.
Actually, I had a good night's sleep last night. The night before, I had clear skies.
Oh. I'm gonna reshare my screen here, I guess, unless somebody else wants to, but I have the full slideshow.
Tilt that down a little bit. There we go.
Let me try that.
Yep, so the sessions are you're welcome to start early if you want, but you're also welcome, Jerry, to go and have your own tea or coffee or whatever break you need. Everyone's just gonna be hopping into the
Got a
session
glass of water.
to start at 20 after the hour. So
Actually, I got a picture.
everyone who's hosting can feel free to take their own break too.
Wait a minute, I'm looking for that. Yeah.
Actually, yesterday's sessions, I was operating on about 3 hours sleep.
Oh,
wow.
So it was clear.
Yeah.
Here we go. Now we don't have to look at our faces big. I think. Hang on. Share. There, we can just let that go. Right?
Yep. You can keep it running and that's fine.
Yeah. Now, if I bail out, if I just hit leave, that just takes me out, but doesn't wipe out your webinar, right?
Right, because you made Jerry the host.
Good. Okay.
And then I can share my screen if I need to.
Yeah,
Can
definitely.
you steal it from me, or do I have to stop? Oh, if I leave, then it's
When you
gonna
leave,
stop. So I won't leave until the break is over.
that would be great if you can stick. Yeah,
Yeah,
stay.
no problem.
It just makes it easier.
Yeah. Now, Lindsay, does anyone else, are all the other sections okay? In terms of,
I'll be looking when it's time for them to start.
okay. And then if you need me to do anything, just,
Because some people may be starting the webinars, kicking them off early, just to make sure they can run them. Others might just be starting on time. So I'm gonna go around and make sure.
great.
I think yesterday with short period pulsars is we were about 6 to 8 people on average. At one point,
Oh,
we got
Friday.
up close to 12, but we never had a big crowd.
Yeah, we had about, I don't know, about the same for the solar too. We had lots of interesting discussion, but not a lot of it was about sunspots either. Chasing eclipses, of course, and
I know, I heard cats were the topic at one point.
cats, all sorts of things.
So if you do want to start early, I'm just going to promote everyone that's left in this session to a panelist, and then that makes us more like a meeting. Everyone can jump in with and just speak as they'd like. So you'll be getting notifications, all of you who are left, that you're being promoted to a panelist. You'll notice when you jump in, you might not have audio right away. If you have a red line through the microphone icon at the very bottom left corner of your screen, that means you don't currently have audio. You can click that microphone and that will give you audio.
And we will, I will adjust the chat settings so that people can use that as well for the EB session.
No, don't.
No?
I wouldn't bother because everyone can talk.
Okay.
Because everyone has audio.
Yeah, all right.
But that's up to Jerry, actually.
No, that's fine. I just want to keep it as open as possible.
Yeah.
All right. So
Well,
yeah.
Yeah, that's right. We'll use the Q&A instead. That's right. We decided to do that. I'm looking at my notes.
And then, of course, anyone is welcome to come and go from this session and all the other sessions as you please. So if you want to go to more than one session breakout, you definitely can.
And speaking of eclipses, I was planning on going to Argentina next month, but I still don't think they're allowing anybody from our country in.
No, we were planning to go as well, and we had booked on a tour, and about a month ago, they said if you still want to go, pay more money, and you can't get your money back unless they cancel on you. So we were not very happy with that because we decided we weren't really happy with their safety protocol. And it also just seemed ridiculous to be paying more money to let them have it until they decide to cancel. And it's just kind of weird. Then they set up other different tours than what the one we had originally booked. So we wouldn't even have gotten to do what we originally thought we were. So we're not too happy with Astro Trails. But anyway, there we are.
Oops.
Yeah, it is disappointing. We really were looking forward to that.
Especially because this is one of the 3 Ceros that I've never seen.
Oh, Terry. Yeah, too bad.
Rob Stevens said Argentina is opening, but lots of health restrictions. Astro Trails has reactivated their tour.
Yeah. Yeah, but I don't know. It was supposed to go to Chile too and include a cruise and a whole bunch of other things.
Well, I pretty much shut down any prospects because in another week or so, I'm going in for surgery.
Oh.
It's pretty minor, but I'll probably be in pain for a while, so I doubt it if I want to travel.
Oh God, yeah. Well, I hope it goes well.
Yeah, really.
It's orthoscopic. It's pretty small.
Okay, good.
That's good.
Although next year's eclipse will be a lot more difficult to get to.
Yeah. That's Antarctica, is it?
Yeah.
Oh.
Yeah, I think we're gonna have to wait till 2024.
Yeah.
I see we're picking up people here,
Yep,
but all their microphones are muted.
that's right. Well,
No, they should be able to unmute, right?
I'll work on that, Jerry.
Okay.
Actually, they can, yeah, I'll work on that.
They're expecting eclipsing binary. We're talking about solar eclipses.
Right, this is going to be the eclipsing binary section, just in case you're, if you're in the right room, you are. Eclipsing binaries.
It depends on where you are located.
No, this room, this space.
Oh, I'm talking about it. A solar eclipse could look like an eclipsing binary.
Oh.
Maybe. No, not quite.
No.
Exoplanet, depending on where you are.
Exoplanets, right. So
technically speaking, the sun can never be eclipsed. The sun can only be occulted.
Yeah, that's true.
So for people who are here for the eclipsing binary session, it's still a few minutes, but if you want to, everybody's muted right now, and just gonna, 1 second. We're gonna give you the power to talk during the meeting, so let's see. I'm going to allow you all to unmute yourself. So now, those of you who are here for the EB session, if you want to speak, just go ahead and unmute yourself, and then you can talk and ask.
Okay. Can you hear me? Okay.
Yeah, I hear you fine.
Okay, excellent.
And then when you're finished with your question or your comment, please mute yourself again so that we minimize the background noise. Please.
They can turn their videos on too if they want, right?
Yes. And yes, you can also start your videos if you want. You all have that capability. So Matt, we both see and hear you. And Pradip, there you are, back again. Good.
Hello.
Hi, Pradip.
How you doing?
Yeah. Can I talk with Jerry sometime?
You're talking to me right now.
Hello.
Yeah.
Hello.
Go ahead, Pradip. You're
Hello,
talking.
Jerry. How are
Yes.
you? I am Pradip from India.
Yes. Hello.
Okay. So, can I talk about our project or extensively on eclipsing binaries?
If you want to talk about a Cepheid, I guess that's okay with me too.
For a couple minutes, but then we should probably stick to EBs.
Yeah.
That's what the group is for.
Okay. So
maybe at the end, Pradip, if Jerry wants to stick around, you could talk about Cepheids.
Okay. Yeah. So Jerry, so far we have worked on SVMON, and we have collected all these data set from AAVSO, visual photometry. So in next work, can I start to TMON?
Yeah, that'd be fine.
And in that case, if you don't mind, I have make a search on AID. You have several data sets. Okay, so first of all, let us start with the visual photometry of TMON from AAVSO archive dataset. And in that project, if you I would like to use the dataset from CCD. Think about this?
That's fine. Last observing season, I observed TMON and SVMON in 4 filters.
Okay.
In fact, I'm also observing it right now, but I haven't posted that data yet. I'm just getting started on the light curves.
Okay. So let us start first with visual photometry from AAVSO archive, and after completion of this analysis, we can include the CCD photometry, which you have been collected.
Now that's fine. When you do build the light curves, though, instead of doing it by calendar year, I would do it from July through the following June, because then you would have one observing season grouped together.
Can you tell me once again the year? Which year?
Well, Monocerotis is a winter constellation, and so the observing season is the later part of one year, followed by the beginning of the following year.
Okay, okay.
And so it's better to group that into one light curve than doing it by calendar year.
Okay, thank you. And one another thing that is my eagerness, that how the CCD generally processed to get the final data set, which has been uploaded to the AAVSO archive.
Well, all my observations from the last observing season have already been uploaded. They're in AID right now.
Okay. And what method is generally used for this type of particular data set reduction?
I didn't understand that. Maybe we should have this discussion offline because we've got quite a few people now on the Eclipsing Binary.
Okay. It's okay. It's okay. Okay. Thank you. Thank you.
So I'm going to, since we're going to start the Eclipsing Binary session now, I'm going to disable chat. And if you have questions if you need to communicate something in writing, or if you have a question, just speak it. But the question and answer option will be there if you want to put something in writing, or if we want to share a link. So I'm just because we don't need chat because we're all talking to each other, and that will encourage us actually to speak rather than to sit there silently and print things. So the whole idea of this session is it's free form. It's talk amongst yourselves, ask Jerry questions, or yell at Jerry, or make fun of Jerry, or just, just you're here to, because you all love Eclipsing Binaries. So take it away, Jerry.
Well, that's it. Whatever you guys want to talk about is pretty much open forum. Although right now it's everybody's got their microphones muted.
Right. So no, everyone should be able to unmute themselves, and right. You can all unmute yourselves to talk. You can all show your video if you want.
Okay, so I guess I'll go ahead and start. So did a lot of people here catch my talk on Friday?
Yes, I did.
Okay. So eclipsing binaries are kind of like, they're the area that I'm really researching. So yeah, this is a discussion I kind of want to have. And I also, want to talk about, if you have questions, I have lots of targets that I would like, that I think are really interesting and that people can observe. So, if you want to ask me questions about that, feel free to.
Okay. I guess I personally have my own list of targets, but if you want to, post them or, ask for help, that'd be fine. Maybe we could do something with the website. Anybody else? I see everybody's still muted, so.
Gary, how do you get started in this?
Well, if you've never done an eclipsing binary, I strongly recommend you start with the legacy program, because those stars have got the best ephemeris, and we can give you a pretty accurate prediction as to when they will eclipse. And in general, you want to get on it an hour or two before the predicted minimum and observe it for a few hours, preferably filtered CCD. We do have observers who use DSLRs, get good data that way too. And then basically you run it just like you'd run any variable star. You'll process a light curve, send your data to AID, but send me a copy and I'll go ahead and do a time of minimum reduction. I'll send you back an O-C diagram showing how your observations fit in with other recent data. And that'll give you a feel for how accurately you're doing it.
Thank you. Somebody asked what a O minus C meant, and now what you just said, it reinforced to me what that actually means.
Okay. O minus C diagram, observed minus calculated. What we do is take essentially a linear equation, period of a star and some reference. In this case, we would use a time of minimum. And if the star gives, if the data basically gives you a horizontal line, the period's constant. If the data gives you a line with a slope, but it's still a straight line, then the period is still constant. You're just using the wrong period for your baseline. If the period is showing a curve, then the period, or the O minus C shows a curve, the period's changing.
Makes sense. Thank you.
We get quite a variety of O minus C diagrams. One of the most unusual ones is if you get a star with an elliptical orbit that has a apsidal motion, and both the primary and secondary eclipses are visible, you'll actually get two sine curves that are mirror images of each other. One will be the primary, one will be the secondary.
Okay.
Do you have any recommendations as to optimum cadence of the observations?
Actually, it depends a lot on the star itself. We have one star that I observe fairly often, UX Ursa Majoris. The entire eclipse lasts about 45 minutes. So in that case, you want the most rapid cadence you can get. But you might get a star with got an eclipse duration of many hours, then you can slow off a little bit. But most observers do it take an observation every few minutes. Once you set up and run, you might as well just let it run.
And I really enjoyed Matthew's talk. And do you generally like a little bit higher cadence because to try and get all the dips and weirdness going on?
So I'm actually using instruments like meter-sized telescopes, like at Kitt Peak and on the Canary Islands, and the cadences I usually run are typically like a few tens of seconds. But I'm also looking at systems that mostly have periods of under a day, so the eclipses themselves are, an hour.
Mm-hmm. I typically run fairly fast cadences. One issue is if you get any kind of weather issues, the more points you have, the easier to throw out the bad ones. You even get the occasional meteor or aircraft flying across my field. Things like that happen. You just deal with it. I guess the basic bottom line would be more data is better than less data.
Yeah, I've done one or two a while back, and I'm getting ready to sort of crank it back up again and looking. And it seemed like the AIA was kind of a strange place to put in high cadence data, but I guess it works just as well as any other.
Well, as was said, some of these eclipses are pretty quick. Most of the contact binaries, the eclipse might last 2 or 3 hours. So that's still relatively short.
So what type of orbital period lengths do you typically like to look at?
Well, the legacy program, we go as short as a few hours up to a number of days. These are just stars that have been observed, going all the way back to when Joe Ashbrook was the editor of Sky and Telescope. He started a program promoting eclipsing binaries, and then that is what started the Eclipsing Binary Committee within the AAVSO. And some of these stars, we've got 50, 60 or more years worth of data. And my main interest is just to keep observing these stars and monitoring all the different changes of period that go on. If you watch a star for half a century, it's amazing how much you'll see.
What type of brightnesses are these stars in this program?
Well, obviously the brightest we have on the legacy program is Algol, and probably down to 14s.
That's actually a bit fainter than I was expecting. A lot of my stars are in that range too.
Well, and a lot of these stars down to 14s date back to the old visual era. We did a lot of those, with the eyeball. Visual was the predominant way of observing until the later 90s, and then the CCD thing pretty much took over. And nowadays, for the most part, we cover it pretty well with CCDs. So we really haven't been promoting visual observing. Well, I will say they are fun to watch visually because you can see some pretty rapid changes.
So I'm going to share a slightly different topic. I'm doing this per my prerogative, even though I'm technically not in this section, because I can. Does anybody know what this is?
That is a heartbeat star, isn't it?
It is a heartbeat star. Now, the reason this one in particular is interesting is twofold. The first reason is this period is 75 days. So that means that you see that it's a very long period system, and yet you still get a heartbeat that's visible in assassin data for an 11th magnitude star. The other reason that it's interesting is because you look at the size of this heartbeat, it's a 1/10 of a magnitude. Now, that's interesting for two reasons. The first reason is that if you were to look for heartbeat stars anywhere in literature or anywhere else, they didn't really exist as a thing until 2012, when there was a paper published from Kepler data. The reason for that is because most of these stars happen to be very, very small. Your typical heartbeat signature is going to be less than a millimagnitude for any reasonably sized star. So any main sequence star, any M star, A star, K star, it's going to be very, very tiny. Even with a very high, even with a low period, let's say like 10 days or less, your signature is going to be barely visible in almost all cases. The only times they get to be large enough that you can see them in your sort of, not by eye, but with normal photometry is when you have these massive stars like O stars. You can see an O star with a heartbeat at maybe a couple of percent. You tend not to get signatures like this, especially on timescales like this, unless you have a supergiant. So big puffy star makes it very easy to distort. But this star doesn't fit any of these molds because everything about this star says that it is not very big. And the signature for this star, if you plug in the parameters that are known about it from spectroscopy, says that this heartbeat shouldn't be there. And yet it is. So we have kind of a conundrum on our hands because two stars that are around 25 solar radii can't make this signal, and yet somehow they do. So yeah, that has been the most interesting star that I have seen recently. And I have absolutely no idea what's going on with it. But, it's fun to look at.
If we're sharing interesting particular stars, there's one that I found that I in my research that I still don't know what's going on. And that is this star right here. Can everyone see this one?
Yeah.
Apparently, this is two red giant stars. This comes from the Villanova Kepler catalog. But I don't know what's going on here. So this one's also really interesting.
mean, there seems to be one eclipse.
I mean, there's two eclipses.
Yeah.
Yeah.
There's probably a secondary eclipse. I wasn't necessarily sure that I would consider the thing at 0.6. Like if I was just looking at it, I wouldn't be like, oh, that's obviously an eclipse. But since the one at 0 is an eclipse, I could be like, well, this is 0.5 away, so I can believe that's an eclipse as well. Have you tried to take away the long-term variation to see what the light curve looks like without it?
So this is actually like an averaged. So this is like splitting it up into 1,000 bins and taking the average of each bin, because the actual data looks a lot weirder than this, or well, not a lot weirder, a lot more scattered. But no, I haven't tried to remove any long-term variations, but it seems like this is kind of like its average sort of mode.
Yeah, I got nothing. I don't know anything that would look like that. Unless it's just a gigantic pulsation mode, but the pulsation mode dominates over the eclipses, which is not impossible, but unlikely.
So yeah, that's a weird one. I just wanted to show that one off.
Actually, it's kind of strange to think about the that being a pulsator, because that would mean the period of pulsation and the orbital period are the same.
Yeah, that would also be weird.
Yeah.
What I honestly suspect going on there is just gigantic, and I mean absolutely gigantic spots.
I mean, you're talking about a change in light of 50%. I mean, the spot would have to be like large and like very dim to get something like that.
Yeah, but it's the only thing I can think of. So.
Yeah, I mean, I don't have a better explanation.
Now the spots would have to cover well over 50% of one side of the star.
Mm-hmm.
Anyone else have any interesting light curves they want to share?
Anybody else have any other comments in general?
Do you have any questions about how do you reduce the data on an eclipsing binary to find a time of minimum? Or do an O-C study?
I don't have a question about that, but can I ask something sort of related?
Sure. You can ask whatever you would like.
Sure. So in the work Madelyn and I are doing, our primary target is a TESS star, but we identify the VSX stars in the field of view. For the one that Madelyn showed in her talk, the AAVSO sequence, the sequence team added a few comparison stars for me closer into the eclipsing binary, but the star isn't centered in the binary isn't centered in the field. It's off in a corner of the image. So can we send like a really detailed request to the sequence team saying, could you find us some comparison stars in just this quadrant near the target, or is that a problem we need to try to solve on our own?
You could certainly ask the sequence team when you have specific requirements for something. They may or may not be able to accommodate you depending on what photometry is available. But certainly if you need something that's not what's already there, let them know. Let them know.
Okay, thanks.
Sure.
Actually, I have in the past sent the sequence team requests where I've sent them a chart and basically identified certain stars or magnitudes for these available, and in particular with each wavelength that I'm asking for. So you can ask any specific question you want, but it's a matter of what they can do.
And something sometimes that I've done when I'm looking at this data is I'll go on Vizier and just look at kind of stars around the variable and see if any of them have APAS data listed in Vizier.
So we do have a bunch of APAS comparisons in the field. It was more wanting to use an AAVSO sequence as the comparison stars for reporting the data.
Right, yeah, it may be that the sequence needs to be tweaked for your target specifically, rather than for something that it may have been created for that was very close by. Something like that, but definitely let them know that what your needs are and explain why, and they'll help you if they can, I'm sure.
Okay, thanks.
Sure. But that's a great idea if they can't do anything. Matthew, what you suggested to get the APAS magnitudes directly from Vizier. The good thing about using the APAS magnitudes is that they're, especially if you note them in your observations, is that if the magnitudes are revised at some point, they can be changed. In your observation, they can be changed because we know what you used.
Kind of like tangentially related, but on what we're just talking about, is there any sort of knowledge about a future release of APAS and APAS DR11?
Oh boy.
You'll have to ask Arnie about that.
Yeah, I don't know what the
You
status.
can go to the BFM section and bug him if you want. I'm sure he's in there.
Yeah, I'm sorry, I don't know the status of that either. Arnie is the person to ask about that.
I'll go with you if you want to ask.
If you wanted to pop over to the Bright Star Monitor session, the link to it is on the AAVSO website link with the /links. And it looks as though he did. That's good. So I have a question for all of you who observe eclipsing binaries. Why do you like to observe eclipsing binaries? It's not just a question to ask a question. I'm genuinely interested. What about eclipsing binaries really makes you just want to follow them?
It's fun.
I would say because you get at least a little story in one night generally. So you get not just, oh, there's a magnitude, but you get a curve, you get something you can, a story you can make out of that curve, and then that can hopefully be integrated into a much bigger story. But with one night, you actually get kind of an analysis that you can do in a result, not just a little number.
Actually, that was the reason I originally got interested, was the fact that you could generate an entire light curve in one night. You could see the action in one night. But that was almost 50 years ago, and I guess now I'm interested in the long-term evolution of these stars. I've seen enough of it happen in my own lifetime.
Well, also, and then you can get really, really weird curves. So I want to try and get some of Matthew's stars dancing all over the place.
Well, one of the more unusual stars I observe is UX Ursa Majoris, because it's a cataclysmic variable in addition to being an eclipsing star, and it's got a period of under 5 hours. The eclipse lasts about 45 minutes, but the eclipse, especially at the end, is very asymmetrical. And I'm wondering if that's when the star comes out of eclipse, is the hot spot on the accretion disk still being eclipsed, and it takes a little longer for that to come out.
Hello.
Yes.
Hello, Jerry.
Hi, Pradip. Go ahead.
Can you hear me? Yeah. My question is to Jerry.
Okay.
Actually, I'm also interested in Lyra variable. So is there possibility to some light curve analysis like say feeds in RR Lyra, that is period change analysis?
Well, the period change analysis is actually, you're looking at O minus C diagrams, so it's very similar to what we do with the eclipsing binaries, Cepheids, any other type of star.
Yeah.
I've seen people do O minus C diagrams for Mira stars, and you can learn a
Actually,
lot about.
okay. Actually, I have seen your several papers on time of maxima for RR Lyra and binary variables for time of minima. So that is why I am interested to know, is there any possibility to do some work on binary eclipse with respect to time of minima to find a O minus C diagram, that is the analysis for the period changes like Cepheids?
As far as eclipsing binary stars, there are two very good databases available. One is run by the BAV, the Liquid Connector database, and then there's another one run by, it's called O minus C Gateway, and that's run by the Brno people. And each of these databases, you can select a given star, it'll generate an O minus C diagram. You can change light elements and see a different O minus C diagram. And you can also download the entire list of times of minimum that they have in their database, which will include AAVSO because we do cooperate with these other organizations. So that information is available online. And if you look at the Eclipsing Binary website, there is a page with some links that'll take you to these various databases.
And one thing is that you have said just earlier that binary eclipse observation generally done within a one night time. So this type of observation is same for the RR Lyra variables?
In general, yes. Most our Lyra variables have periods close to a half a day, some are shorter, and they can all be observed within a single night. You won't get the entire period, but you get enough to work with.
Okay. So, so can we try to study the period changes of RR Lyra like Cepheids?
Yes, there is another database for our Lyra's. It's run by the GEOS people, and you'll find a link to that on the short period pulsator page.
And last one is with respect to time of minima of eclipsing binaries. I would like to try to find out the time of minima using V star software, which I have used. You know it well that for the case of SVMON, I have used a V star to find out the time of maxima. So is it possible, or let us try?
I don't know if that, I've never worked with that software. I use a program called Parenzo, available, it's a very economic program to buy, and it's got a Qui Van Worden routine built in for doing eclipsing binary analysis. It also has curve fittings, polynomial fittings for doing RLA arrays. It's a very powerful program, covers just about anything you want to do with any type of star.
And with respect to your suggestion, I should follow the Piranso software to find out the time of minima.
Say again, please.
I have read out your several papers on eclipsing binaries also. In almost all the papers, you have used the Piranso software. Yeah. So
that is correct.
And KW method so far. I have read out your paper.
Okay.
Can it possible to, let us say, attempt to cross check to use the V star to find out the time of minima, which you have find already, and using the Piranso What is your suggestion?
That certainly is a possibility.
Yeah.
In fact, just to back up a little bit, when I do the analysis with defined times of minimum, I will typically not just take one data interval, I will take several different groupings of observations, generate several different times of minimum for one light curve, and then just see if they all tend to cluster in the same place, or if there's any kind of variation depending on how clean the light curve is. So it's not a real cut and dry process. You do have to do a little bit of analysis there. And you do also, I like to do some cross-checking along the way to make sure that what I'm doing really, it looks right and makes sense.
Which period running routine do you typically use in Paranzo? Because I also use Paranzo, but I'm a fan of using ANOVA.
I haven't really used any of the period finding routines. I've played around with them a little bit, but my main use is to use the Qui Van Worden routine. And I also use a polynomial fitting because I also work with our Larius and Cepheids.
Thank you.
So I also wanted to share with anybody who is interested in doing binary analysis with, or eclipsing binary analysis, that the newest version of Phoebe is now live. Phoebe 2.3 includes a GUI. You can even check out the GUI online if you'd like to just see how it works. I'll post the link in the chat. And it also has support for fitting. It does multiple different optimizers that you can use that all have the same format. It does, it has samplers such as MCMC, and I think maybe nested sampling as well. I can't remember, but it's a lot cleaner for using it for any sort of analysis and finding binary parameters. So if you are interested in checking it out, it's a lot easier to use now. I will not say it is easy to use, but if you have questions, please feel free to ask the VP team or me in general, and I have no problems helping out with stuff like that and getting things working.
One question I did want to ask about that, because I was at the Phoebe workshop last summer.
Mm-hmm.
And I know back then you were still kind of working on implementing, I think it was either over contact or semi-detached. Has that work been completed?
Semi-detached, yes, for the most part. Over contact, not entirely.
Okay.
There are lots of reasons for why. The main reason is because we don't really want to cheat, or we want to cheat as little as possible, and none of the ways that it's currently implemented in any of the codes is in any way correct. So they're trying to get it at least moderately correct. Angela's been working on that for a while. She has made quite a bit of progress on it. The sort of, it will load, it will do things correctly, and it will sort of auto adjust and tell you why if the contact isn't working. Now a little bit better. So if it just couldn't find the shape correctly or something, it will let you know that you need to like up your number of triangles or this or that. So it's a little bit smarter, but I still wouldn't rely on it for science yet.
Okay.
Let's try sharing my screen here. There we go. This is a light curve that I observed just last week or so. And I was wondering if is this a example of the O'Connell effect, or is this a
yes, it is
something else?
And it's also has an asymmetric minimum, which is like this increases the number of systems we know that show this like another 10%. So so you took this data yourself?
Yeah, this is on the 6th of this month.
Do you know of anyone else who has published any papers on this, or?
No, I don't.
Okay.
But I know that this star has been fairly well observed.
Okay.
Within the AAVSO, so there's quite a bit of observations in the database.
Yeah, that is very those are the types of systems I'm really looking for. That's one of the reasons why I brought it up in my talk on Friday. So
Well,
thank you
I'll
for
have
showing
to
me
take
this.
a look through my archives to see how many more of these I have.
I'll just throw in something here. Gary Billings speaking. I don't know if you can hear me.
We hear you fine.
Okay. A number of people were asking about O-C diagrams. Last year at the fall meeting, at the how-to hour, I gave a talk about O-C diagrams, and I don't believe that talk was recorded, but I did post my PowerPoint to the Eclipsing Binary forum. And if you are looking for it and can't find it, I guess just post a request and I could repost it. It's, you know, it was for a 30-minute talk about what are O-C diagrams, and particularly useful might be the resources pages in that PowerPoint that list other readings, including, there's a whole book about O-C diagrams. It was an Astronomical Society of the Pacific Conference Series Proceedings volume called The Light Time Effect in Astrophysics, Causes and Cures of the O-C diagram. And the first couple of papers are very overview tutorial, and they're actually available from ADS, so you can download them for free. Another resource is back in May, we gave an online webinar. I guess it was the first experiment with a Zoom meeting about, and it's available on the AAVSO YouTube page. It's called How to Plan Observing of Eclipsing Binaries When Ephemerides Are Out of Date. And Jerry talks about legacy stars, and I talk about working on stars that are not well understood, whose light elements are not well determined. So that could be a useful reference as well, a useful resource. That's really all I wanted to say.
Actually, I'll say that presentation on O-Cs is very good. So I strongly recommend that to anybody who has any questions.
Hi, this is Craig Babbage. What are some good intermediate books, texts that are on eclipsing that aren't too high up into astrophysics, but aren't the beginning level either?
That's gonna be tough. Mainly because
I'm thinking, I don't know where you would maybe put the Calrath and Malone 1999 book, if that would be in the too advanced category.
I like that one. I would say that it's, they actually have an update of that's from like 2006, 2008. It's just Physics of Eclipsing Binaries. They don't go into, I mean, they do go into math, definitely, but they kind of like go into it from a perspective of like, here's the sorts of things that you can get from an eclipsing binary. I would say that it's upper level intermediate, definitely not a graduate text, but maybe an undergrad text level. So, but eclipsing binaries is just so specific that it's going to be hard to find something that is sort of above the sort of basic level, but then below the advanced level. There's just not a whole lot of in between there that I can think of. That may be the closest one. Let me see if I can find a reference to it, and you can at least see if that's what you're looking for.
If I can jump in while you're looking for that, Bert.
Sure.
There's another book that I like. It's called Introduction to Astronomical Photometry. And the title, well, the title is actually broader, or the book is broader than the title. It's not just about how to do photometry. For example, one chapter is about period changes of variable stars, and it discusses O-C diagrams and what causes period changes and so on. It also covers quite a bit. I think there's a whole chapter about eclipsing binaries, and talks about, gives you lists of eclipsing binaries that are known to be in triple systems and how that's known and that sort of thing. So it's by, the first author is Budding, Budding, and it's published by Cambridge, 2007. So it's not going to be a cheap book, and it's a bit obscure, but I find it quite readable. You know, it's sort of middle undergraduate level. One thing I like about it is each chapter has, as I recall, yes, an annotated bibliography where they list their references with commentary about what this reference is particularly good for. So that's a suggestion.
Thank you.
Thanks.
Anybody else? Any comments, questions?
How many filters would you typically be comfortable? Like, do you typically observe your eclipsing binaries in, Gary?
I usually go V-band.
Just V-band?
Yeah, I really don't have a setup where I can be swapping filters while I'm doing a time series. In fact, 3 of my cameras, I only have 1 filter screwed into the nose piece, so I can't change filters. Then I have 1 camera on a scope with a filter wheel. Then I got a couple of small rigs. One I call camera on a stick. It's basically a camera with a 50mm lens. It gives me a 10-degree field. That one has a filter wheel. And then I have another rig that gives me about a 2x3 degree field. That one has a filter wheel also. But those rigs have absolutely no automation. That camera on a stick doesn't have a clock drive. I just point it and shoot. I originally set it up for Epsilon or IJ. And I found there's a whole bunch of bright variables I can do that, 30-second exposure or less.
I also observe single filter. Partly it's, filter wheels can be problematic. They're extra cost. And I'm looking for time resolution, not, I'm not trying to transform my data to make sure my magnitude levels are completely consistent with everybody else, because my purpose is getting the time at minimum. There was some interesting discussion about that yesterday on the instrumentation forum, I think, that sort of dichotomy between different observing styles and goals.
Typically, as an astrophysicist, my goal is of the modeling. So for that, I kind of need not just good magnitude, but also for temperature, I need multiple filters.
Right.
I think the only stars that I've done multiple filters on are the very long, like EECPI, where I have time to shoot all the filters in a given night.
What are your
Sonodride,
Oh, sorry. What are your
IJ, Beta Lyrae, those type?
Sorry, Jerry. Matthew, what are your preferred filters for people to use?
Typically, like I observe BVRI, that might be kind of overkill. I know that Bob Barrington, back when I was at Ball State, he typically just did BVR, and I think that that's probably like the best kind of setup is to do those 3. If you can get away with I, if you can get away with U, I mean, it's extra information, but of course you reduce your time resolution.
I would say it depends also on the type of star that you're looking at. For instance, if you're looking at a massive star, which is bluer, if you can get U, you would definitely want it, and I isn't necessarily that interesting. Whereas if you're dealing with like a much lower mass star, U is going to be very difficult to get and also not really that useful for the most part. I won't say it's not useful at all, but just in general, That's kind of how I would look at it. If you could get U on massive stars, they love that. U is very, very difficult to get though. So,
yeah,
you know, maybe it's not worth it.
And with I, at least with the instruments I'm using, I have to deal with fringing interference patterns. So that adds another wrinkle into things.
I only own one U filter and I have never been able to get repeatable results with it. I'm probably too deep in the atmosphere.
Hello.
Yes.
Hello, I am Pradip. Okay. I want to know that Cepheids and RL variables are important to find out the distances of the host globular cluster. For this point of view, the observation of Cepheids and RL are very much important, and also for the find out the physical parameters like temperature and another thing. My question is, then what is the importance to observation for binary eclipse like this?
Hello, Pradip. This is Gary Billings here. I'll
Yeah.
take a stab at
Thank
that.
you. How are you? Okay, fine.
I'm well. How about you?
Yeah, I'm fine.
The eclipsing binaries are they're a bit like Cepheids. They're useful as a tool. If you have an eclipsing binary and you understand its orbits and its light curve, and you have radial velocity data, and you can make a model of it using Phoebe the way Bert described, what you can get a tremendous amount of information about the system. You can get absolute dimensions and masses for the stars that aren't based on any approximations or assumptions or correlations. They're near enough to being a direct physical measurement. So that's why eclipsing binaries are traditionally so interesting to astrophysicists, because they're the only types of star systems where you can directly measure those things.
And
another thing that you can get is not just like the size and dimensions, you can get the actual shape of the stars.
Okay, in the binary star system, generally, I have not yet worked, just read about things, some papers. Is it possible to find out the mass and another characteristics of both the stars, or only for primary or secondary stars?
That depends on what information you have. So it kind of depends. To get masses, like really with any real, you need to have spectral data. You need to have radial velocity data. That's how you get the masses. And it's going to depend on if you can get the radial velocities for both stars or just one of the stars. Obviously, if you get it for both stars, you get more information, but...
And in the light curve of eclipsing binaries, which have been presented in presentation or workshop of binary eclipsing, which I have seen so far, actually I have actually no knowledge about this field, but I am very much interested in this field. So that is my question, that the light curve which has been showed with respect to, or for the purpose of eclipsing binaries, that represent the primary star or secondary star?
It's a combination. You can't split them out.
Oh, yeah.
Right? So when you see an eclipsing binary, typically speaking, there doesn't have to be, but in general, there are two eclipses. One, when the primary star is blocked by the secondary star, that's typically the deepest eclipse. It doesn't have to be, but 9 times out of 10 it is. And the second is when the secondary star is blocked by the primary star. The stars are so close together that you're never going to get information on just one star or the other. Everything you get is a mix of both stars. I mean, it is theoretically possible that there's an eclipsing binary for which both stars are resolved, but it needs to be an extremely wide orbit. And when you have an extremely wide orbit, it means that you're most likely not going to eclipse. So almost always the data that you see will be from both stars.
If any system was going to be resolvable, it would be something like Epsilon Auriga, and I don't know if even that one is resolved.
After seeing the response of Bart Pablo, can we say that the light curve is a combination of primary and secondary stars? Am I right?
Yeah, that's
Okay.
almost always accurate.
Okay, so that means the observation system of Cepheids and RL Lyra is different from binary stars observation technique.
No, the observation is identical. We're measuring the brightness of either a single star or a system.
Okay.
We're doing the same type of photometry.
For both cases, if you were looking through a telescope, you would see a single star, whether it's an eclipsing binary or a Cepheid. And same with images, your CCD images of an eclipsing binary system, you're just seeing a single,
Single source.
Yes.
Spot.
Yes.
Yeah.
Yeah,
Oh.
that source just happens to be two unresolved objects.
Yes.
Okay, and Gary, I have a question related to this purpose. So far, I have done the analysis of variable stars, mainly W Virginis stars. I have used the Dowford package of Stetson 1987, and for the binary eclipse, as you said, that for the technique has been used to check star and comparison stars to find out the final measurement photometry of the binary eclipse. And so is it possible to use the same technique like Dowford to measure the magnitude of the binary eclipse? Is it there is any possibility? Yeah.
Yes, because once again, in the images, it looks the same. It's just a single source in the image. Your photometry program doesn't know that it's an eclipsing binary or it's a Cepheid or it's something else. It's just a single light source.
Yeah. Okay. And in the use of photometry, Dowford, finally, the the measurement which have been made by the telescope, that is to be finally transformed into the standard form like Dowford, Landolt system. And in the case of binary eclipse, generally it has been used comparison stars and check stars like this.
I'm not sure what your question is.
For the reduction procedure, for the case of when we use the Dowford system, after reduction, we get the magnitude of the corresponding Cepheids or RL Lyra, just the instrumental magnitude. And after that, we have to transform this into the standard magnitude using the standard magnitude like Landolt system, standard stars magnitude. And for the case of binary eclipsing, so far I have studied that generally to get out the final magnitude of the corresponding eclipsing binary magnitude, generally use the comparison stars magnitude. So my question is there any possibility to use the Dowford for the case of eclipsing binaries?
I don't use that program, but I believe you certainly can. It's just measuring brightness in an image, and
okay.
And the program itself doesn't know what the star type is. It doesn't really even know what filter you shot through. So if you're going to do transformations, you're going to be shooting images through different filters through the night. You're going to be alternating between different filters. And you'll be extracting the magnitude of your target and your comparison stars in each image. But as we were saying earlier, most of us who are just getting times of eclipses don't do transformation to standard magnitudes. We just do differential photometry against the comparison star. But as Matthew was saying, I hope I got the name right there, there is a lot of value in transforming onto a standard system, because it allows you to do proper modeling and work with temperatures and so on.
Okay.
It's also easier to upload the data to the AAVSO database if you have full magnitudes and it's not differential photometry. They show up in the light curve generator. They're included in the data download. Differential photometry are not included in those things unless the person specifically asks for them. So it's really better when you're submitting your data to the AAVSO database if you cannot submit them as differential magnitudes, but reduce them to a B standard or whatever the filter is.
Well, what you say is correct. I would like to add to that in that when I do differential photometry with just a single filter, I submit that, and I'm submitting it as untransformed but standard magnitudes. I'm not submitting it as differential, because AAVSO differential is actually something kind of peculiar that I don't think anybody uses much these days. So I'm yeah.
You're right. I hear what you're saying, Gary. No, that's fine. Yeah, the whole definition of standard, it's a little confusing because there's, at least in the AAVSO world, because there's the Landolt standard where things are reduced to the Johnson-Cousins system, which is standard with sort of the capital S, and standard magnitude, which means a magnitude that isn't a delta magnitude.
Yes.
It's a magnitude, for example, 7.0 and not a delta of 0.6, something like that.
Yes.
So,
yes.
Right. So reducing them to little s standard magnitudes and submitting them is great. It's ideal if you can transform them to
Big S. Yeah.
but the least desirable is submitting them as delta magnitudes.
Yes. Yes. And with our apologies to Pradip, because at this point, I'm sure he has no idea what we're talking about.
I know.
No. Actually, I am just like you think as just a student, just admitted in this field. So my knowledge is very much low, as you know this, and all the panelists who are present at this time. And actually, I am far distance from AAVSO. My country is India, and at present situation it is not absolutely impossible for me to avail the telescope facility. So if there is any possibility in future with respect to AAVSO for students like me, I am very much interested to know and see the techniques, how the observation made, like say it may be Cepheids, Aral Lyra, and binary eclipse. And last of all, I must convey my gratitude to AAVSO members, and I gather many knowledge, many helps from the person who are attached with the AAVSO. So I am very much grateful to those who have helped me, and I hope I get this help in future also. Thanks to all of you.
Thank you.
You're welcome.
Please keep asking your questions, because either by email and in the forums, because people are happy to share, happy to teach and to share, and we learn from each other. So please keep asking and keep learning. It's great.
Thank you.
Okay. We're technically at 20 minutes past the hour, which is technically the ending time. Do people want to continue for a bit? Jerry, you're the leader.
Hey, as long as people have any discussion, I'll hang around. It's not like I got a far to drive.
Okay, well, why don't we keep it going for a bit longer, maybe another 10 minutes, and see how things go. See where we are at 1/2 past the hour.
Jerry, just real briefly, could you talk for just like you're doing an observation of one star? What's your workflow?
You were kind of breaking up. Could you repeat that, please?
What's your workflow for doing an observation?
I'm not sure what you mean by workflow. Essentially, before it gets dark, I open up all my telescopes, get my cameras cooled. As soon as it gets dark enough, I shoot my flat fields, and then I'll target each telescope on a different star. I'll set up an autoguider, get that running, and collect data throughout the night. When I complete the data, then I go through and I do the standard dark subtract flat field standard reduction. And then I use Myra for doing my photometry. And I will generate what we described earlier, a standard non-transformed brightness. At that point, I usually will I'll take the results and I'll just drop that into a quick spreadsheet just to see if I got a clean light curve or not. And then I'll take that data and I'll reformat it to the AAVSO format so I can submit it. But usually before I submit it, I go ahead and calculate the time of minimum. And I'll take a look at the O-C just to see if what I did makes sense. Sometimes there might be some type of error that comes along the way. I'd rather catch that before I submit it.
And whose filter do you use?
As I mentioned earlier, most of my data is shot through V-band. And I have a variety of manufacturers.
Okay.
I had been buying Astrodon.
That's exactly what I needed to hear.
Say again?
Okay. That's exactly your description, what you just went through, exactly what I needed to hear.
Okay, great. I'm kind of spoiled because I've got 3 permanently mounted telescopes in my yard. I've got another one I can roll out on wheelie bars. Then I got the 2 smaller cameras. So I can run as many as 6 cameras.
But Jerry, you've been doing that for 50 years.
Wow.
Well, I didn't have cameras for 50 years. I used to do it visually that way.
Yeah, right. Just go from telescope to telescope to scaloscope.
Yeah. This is now I let them guide themselves.
Is out of curiosity, is anybody who's here right now observing visually? Crickets. Okay. So everyone's observing non-visually in this who's right here. Interesting.
I haven't done a visual observation for a number of years. I had been doing it a little bit recreationally. In fact, one of the stars I always enjoyed was Xeris Majoris. But when I commissioned my ST8 rig, I used that as a star to commission on. Well, now that I'm doing with the CCD, well, I watch it visually.
Yeah. I should clarify. I should qualify that. I'm the only visual observer here because I'm a visual observer.
Well, I don't do any eclipsing binaries visually. It's all CCD, but the brighter stars or binocular stars I'll do that are not of that type. Just for fun, just to get out under the stars.
Hello, JD.
Yes.
I'm Pradip. Okay. Can I ask which you have shared me long back in email, if you give me permission, about with respect to your India visit, Gujarat?
Well, the reason I visited India was the company I worked for sold a electrical control and hydraulic system to L&T Corporation in Surat. And my job was commissioning engineer, so I went there to handle the startup and commissioning of the system.
Okay, as you shared to me in your email that in that time you bring your CCD camera, but they are not mentioned about telescope. So my question is it possible for me to take the images, if there is any possibility in the night sky, to take the images of the star using CCD camera or DSLR camera without telescope? I have no conception about this matter. That is why maybe it's a funny question to you. So I want to know about this.
Well, the camera that I took to India was the one I call a camera on a stick, which is a camera with a 50mm lens. It gives me a wide field, but it's limited to about 6 magnitude. So I really can't get very faint, but there are plenty of bright variables that I could shoot while I was traveling. I basically did that because it was the only thing I could carry on an airplane and still do photometry.
Okay, okay. So without telescope, it is much difficult to take the images of the variable star.
Yes, absolutely, because the name of the game is we want to collect light, and the bigger lens you have, the more light you collect, the fainter you can image.
Yeah, and which technique usually was used to visual photometry, which we have used for the case of, say, SVMON data analysis?
Well, as I mentioned, I use the program called Myra to do the reduction of my images. Actually, I use Myra also to do the dark subtract and the flat fielding, calibrating the images.
Okay, thank you.
I'm probably the only person around who still uses the dinosaur that is IRAF. Earlier in this session, we had mentioned maybe something about that some people were interested in a target list that I had compiled. And I was wondering if there was anything you wanted me to do that, because I actually just was kind of working on that a little bit right here, and it's ready to go if you just tell me.
Can you please once again more?
I was saying that there was some interest earlier in this talk, and also after I gave my talk on Friday, about a list of targets that I compiled, of targets that I was interested in, which is about 240 eclipsing binaries. And I've gotten this list compiled, and I was just wondering what I should do with it.
Yes.
Well, I would think the best thing to do would be to find a place on our webpage where we could post that. Maybe we need something regarding special projects, and get a little write-up about why these targets are important, and see what kind of response we get.
Is there anyone in particular I should talk to about that?
Well, I'd like to see a copy of what you want to do, but I'm really not much of a web person. But Sarah usually handles the technical details of getting that up.
Yeah,
that would probably be me or Elizabeth, honestly.
Yeah, Matthew, if you and Jerry can coordinate on the content, and then let, as Jerry said, Bert or Jerry can pass it to Bert or Sarah or me, and we'll make a web page. Sarah has been doing the web page work for the observing sections, so it would probably be Sarah. But
that's great.
Content first.
And can I talk to Sarah Beck for a little bit?
Sarah's not, Pradip, Sarah is not here, but I'm Elizabeth, and I'm Sarah's colleague, and maybe I can.
Oh, yes. Actually, I have written some notes of Sarah Beck, written about V star analysis. And so my question is, I have just a few minutes before asked JD that I have used to find out the time of maxima using V star. Okay. So my question is it possible to use the V star to find out the time of minima for the case of eclipsing binaries? Please don't mind. I understand that you, Sarabek. Please don't mind.
No. You should be able to. Yes, Pradip.
Yeah.
You can do period analysis in VStar, and you can create phase diagrams. So I think you can. I think you should be able to study the period and find times of minimum.
Yeah, I have done and find out the minima for the case of Cepheid's analysis, SV1,
yeah,
which I have been working on with JD. So if you say that this is yes, then I must try to use VStar to find out the minima for the case of eclipsing binaries.
Try it. It's just a different type of star, but the process is similar.
Okay, thank you.
Go ahead and experiment. And if you still have questions, email Sarah. I know you have her email address.
Yeah, yes.
Email Sarah, because she's really the expert on VStar.
Okay.
I use it, but I don't know it as well as Sarah knows it.
Thank you.
You're welcome.
Jerry, it's Jerry, right?
Correct.
Could I have your email so that I could get into contact with you?
G Samolik, spelled the same as my name.
Okay.
At wi.rr.com.
Could you repeat that last part, please?
wi.rr.com.
Okay, thank you.
It's basically Wisconsin Roadrunner.
Okay. And I will get into contact with you shortly about that.
Okay. Any other comments? I know we've run over on our time, but I think this has been a very productive discussion.
Definitely.
And thank you all.
So if we're finished, I'm going to thank all of you thank Jerry for heading this session, and thank you all for attending. And thank you all for attending the whole AAVSO annual meeting. It's been great to see your names and your faces, now to see your faces as well, and to know that we've had so many people from around the world sharing in this meeting. It's one of the advantages of having to have a virtual meeting that more people from different locations can join. And so we've just been delighted to see the turnout. And so I thank you all very much. And I'm going to share my screen. And I want to thank, there we go, our sponsors. Are you seeing that?
Oh yeah.
Okay, great. I can't see that when I share. We want to thank the companies who've helped sponsor our workshops and our annual meeting. They've been very, very generous, and we're grateful to them. Our platinum level sponsors of QHY CCDs and Optical Structures and UBSTech, and our gold level sponsors, First Light Observatory Systems and iTelescope.net. So we thank them all very much. And again, I hope you all had a good time at the meeting and found it enjoyable, and hopefully you learned some new things. I know I sure learned a lot. And we'll look forward to seeing you again soon. And I really hope we'll see you all soon in person. So.
Well, this year we're all getting used to seeing people as little images on a screen.
I know, it's just not the same though. So thank you.
I definitely echo that.
Yeah.
And thank you for organizing all this.
Oh, it's been a pleasure. Yeah. Lindsay Ward and Stella and Bert have
thank you
here, and the rest of us have helped out. But
thank you everyone. Have a nice day.
Take care. Stay safe and
Thanks, guys.
have a safe journey back to your home.
Thank you.
Don't trip up the stairs. Yeah.
And good
Actually,
skies whenever they come around.
You're here.
Mm.
Thank you, Jerry. Bye.
Good to see you.
Well, there was one nice thing about this meeting. I could actually get some observing done.
That's true. We didn't have to worry this time about the dark of the moon.
Yeah.
Yeah. Yeah, normally we'd all be screaming like crazy if they had a meeting during a new moon.
I know. We always try, but once in a while we just don't have any choice. We usually try to have it during full moon, but that doesn't always work. So this year it didn't matter.
I got 9 targets Friday night.
That's great.
Jerry, what is the time about your place?
About 1:30 in my time zone.
1:30 p.m.
1:30 in the afternoon, correct.
Yeah, and my place time is 1:10 night a.m. And actually, I am sharing this. I am just sitting on my dining table, and it is not finished yet. Actually, I have gained this opportunity to share my queries to with you. That is a great opportunity and pleasure to me. I'm very much thanks to AAVSO team, and hope in future students like me who are far distance from AAVSO, it is very helpful for me and like me students. And if there is any possibility in future time in my life, I would like to visit AAVSO. This is my heartiest interest. If there is any possibility in future in my life, at least one time, AAVSO Observatory.
We would be delighted to welcome you to headquarters, Pradip. It would be our joy to welcome you.
And I should share myself something about this. At present, I'm a teacher of mathematics of a class 12 institution. In the year 2005, I've got a chance as a lecturership of mathematics in a college, but due to my bad luck, I have faced some political problem. So for this reason, I came back to my institution, and after that, my journey in the field of astrophysics and astronomy had started, and in the field of variable star have started after listening a lecture in my university, Calcutta University, which situated in Calcutta. I hope Jerry has know about little bit about this university. This is very well known. Anyhow, after listening a lecture on variable star, I do not know. I have been very much attracted, very much attracted. And after that, I have made a huge search in the internet in when I get time in my institution, in the off period, and in my home. And after that, one day I get contacted with respected Horace Smith. It's a God gift to me. It's a God gift for me, and from him I get huge information and suggestion. And after showing the Gary and Jay said presentation on eclipsing binaries, I am very much attracted to both of you. And after hearing the lectures, and I make a search in AAVSO. And before that, I must say something about the AAVSO history. After contacting, one thing, are you feeling bored about my sharing my information?
No, go ahead, Pradip. It's okay.
Okay, so I have communicated Horace Smith in the year 2015, and after that, in the year 2018, he advised me that you should become a member of AAVSO. And after hearing his suggestion, I make a search in the internet about the AAVSO. And one experience I must share about the membership case. When I attempted to become a member using my credit card, this is my personal experience. I faced several problems to transfer the money. And after facing this problem, I shared this problem with Horace Smith, and he told me that, Pradip, please share your password and your information. I pay this thing, the amount. And he do this. And after that, I emailed him that it is a great opportunity to become a member. And I have tried several times to refund the amount to Horace Smith's account, but he did not take this amount. After that, the journey of AAVSO has started, and I get many information and knowledge from AAVSO. And after returning from college to the institution, that means in my institution, class 12 up to standard class 12, many people say that what do you do in off time? What do you search in your internet, in your mobile? Many people say something, what do you get from this? There is no money. There is my one answer to all of them, all of questions, that this is my heartiest pleasure. After getting a chance as a lecturer in mathematics in a college, due to my bad luck, I have lost this. But in the field of astronomy, astrophysics, Horace sir, Gary sir, and so many persons who have helped me very much in this field to know that or gather the knowledges. And one person is also helped me, who is Christine Clement from Canada, Toronto University. She helped me very much to know the knowledge, to use the photon packages like this. And so this about me. Thank you for sharing and getting the chance to sharing my background about the field of astronomy and astrophysics. Thanks. And giving me chance to sharing this opportunity.
You're very welcome, Pradip. I think we all love astronomy. We all love the joy, the satisfaction that we get from working with astronomy, with variable stars. It's like you have. It's just, we do it because we love it. There's no money in it, for sure, but we do it because we love it.
Thank you.
Sure. Thank you.
And this is the encouragement for me to proceed further in this field.
Yeah, good. Yeah, keep up the good work.
Actually, it's funny that you, it's kind of funny that you mentioned that, though, because I also did a lot of work over in China, and all my friends over there, when I told them what I do, they all would keep asking, can't you get paid for that? It's like, no, I do this because I enjoy it.
Okay, I'm very much happy to, that's just you share with me that that means I am not in the absolutely wrong track at present.
No, you're on the right track. You're on the right track. We're all on that track together.
Thank you.
Sure.
And we'll be in contact through email on the remainder of these stars that you want to work on with the Cepheid project.
Yeah. Okay. I'm almost rectified the paper of misprint, whatever written so far. And I am thinking that after actually at present in our state there is a festival is going on. The festival is called Festival of Light, and which has been observed throughout our country, and particularly in our state it is I do not know, do you hear in past Kali Puja after Durga Puja. So I'm a little bit afraid that at the time of presentation there is a big noise problem in my surrounding places. So anyhow, I have overcome. And this year, due to the pandemic situation, the festivals gathering is very much low. But anyhow, it is okay. So Jerry, I am almost ready to this paper in the docs format, and I would like to submit in the AAVSO for the publication. I do not know how far it will go, but I would like to keep contact with you. As you suggested, I have made a little bit try to get some data set from AAVSO archive on TMON, and if possible in the next paper I would like to use your observed data set as you please.
Sure, that's fine.
Thank you.
Well, I think we should probably close this, wrap this up.
Yep.
If that's okay.
I'll see you all later.
Well, I need to shut it down from, I need to shut things down here, so.
Yes, one time, please.
Okay, go ahead, Pradip.
Okay, from my side, good night to all of you with respect to my time. Thank you.
In your case, it'd be almost good morning.
Right.
Okay, thank you.
Good night, Pradip.
Same to you.
Have a good rest
Have
of
a
the
nice day to all of you. Okay, thank you.
Take good care. Bye-bye.
Okay, goodbye.
Bye.
Is there something I need to do to shut this down, or
I
you
can
handle it from your end?
I can do that from my end, Jerry, if you want to make me the host.
Okay. Oh, I just gotta remember.
Jerry
how to
Walker,
do
I
this.
see you there. Is there anything we can do for you?
I'm trying to remember how to do that now. Speaker view,
Go to the panelists,
panelists.
participants. Go to participants. Go to participants.
Yeah, I'm looking for that. Oh, there it is. Okay.
And then click on that, and then you'll see.
Yeah, I remember now.
Click on panelists.
On more.
No, up at the top, you see participants for.
Yeah.
And there's the panelist list and the attendees list.
Mm-hmm.
Okay, click on the blue panelist.
Yeah, I got that up.
Okay, then go to I'm the AAVSO symbol.
Right.
Up and click on more
Yeah.
and make me the co-host.
Got it. Yeah, I know we went through all this, but I have a short memory.
No, that's okay. That's okay. Great. Thank you. So now I can I'll shut it down when we're done. Okay. Great.
Okay.
All righty. Anything else at this point?
No, it's been a good meeting.
I think so too.
A lot of good information.
Good. I think this was a good session. There was lots of good discussion once people got warmed up.
Are they going to make this public?
Yes, in fact, we are still recording, and it will be on the YouTube channel in a few weeks.
That's why I was a little leery about giving my email address.
I think, well, they could, I don't know if we can edit, actually, I'm going to, just a minute.